Let's start at the beginning. What is an ocean planet? When we talk about ocean planet, ocean world, oceanic planet, ocean world, panthalosic planet, aquaplanet, or aquatic world, it is the same thing. All these terms refer to the theoretical model of the ocean planet. For a long time, the idea that there could be planets entirely covered by an ocean seemed like science fiction. For the average observer, ocean worlds were the fruit of the imagination of authors, scriptwriters, and storytellers. But scientists have been seriously considering this idea since the discovery of exoplanets. The discovery of the first exoplanet was announced on October 6, 1995, by Michael Mayer and Didier Queloz. It was named 51 Pegasi b. This Jupiter-like gaseous exoplanet is uninhabitable and very far from us, at a little more than 50 light-years. But its discovery was still a bombshell in the scientific community, because it showed us that yes, there may be other planets in the universe than those of our solar system. Since this discovery, scientists have developed models to describe all types of exoplanets in the universe. Among these models, that of the ocean planet is one of the most intriguing. An ocean planet would be a super-Earth covered with a huge liquid ocean, not necessarily salt water. A super-Earth is a telluric planet like the Earth, but with a mass greater than that of our planet. Watery planets could be 6 to 10 times bigger than the Earth. The oceans of these planets could be very deep, about 100 kilometers or 60 miles according to the models, or even more. Schematically, an ocean planet that moves closer to its star would become a sauna planet because it would be enveloped in a thick atmosphere of water vapor, while an ocean planet that moves away from its star would become an ice planet. Ocean planets could therefore be ice planets that would have migrated towards their star and whose ice would have melted on the surface, thus creating an ocean. In April 2020, a paper by geobiochemist and astrobiologist Donald M. Gliese and his team was pre-published on the ARXIV Open Archive. This article distinguishes two types of ocean planets. The so-called pelagic planets have between 0.2 and 1% of their mass in the form of surface water. For a planet of terrestrial mass, this is equivalent to between 8 and 40 times the terrestrial oceans, enough to submerge the entire Earth. Pelagic planets are to be distinguished from oceanic worlds, which have more than 1% of their mass in the form of water on the surface. This allows for an ocean deep enough to form a layer of high-pressure ice between the rocky crust and the liquid water. You may wonder why ocean planets remain theoretical. It is true that several discovered exoplanets have conditions that are conducive to the presence of liquid water on the surface. But current technologies do not allow us to directly observe whether or not there is liquid water on the surface of an exoplanet. Only atmospheric water vapor can be detected. It is then an indication of the presence of liquid water on the surface, without confirming it at 100%. If ocean planets fascinate us, it is first of all because we thought for a long time that they existed only in the imagination of science fiction authors. And now, astrophysicists tell us that they do exist in the real world. One of the most famous ocean planets in fiction is Camino in the Star Wars series. Camino is the planet where the clone troopers come from, and where the clone troopers train. It is located beyond the outer rim, near the satellite galaxy called Rishi's Daedalus, and orbits the star Camino. Camino is entirely covered in water, but it is home to an intelligent species, the Kaminoans, who supply clones to the Galactic Republic. The ocean planet Camino can be seen in the movie Attack of the Clones. In the series, the planet was previously covered in ice. During various events, the glaciers suddenly melt, creating a watery planet. In the movie Interstellar by Christopher Nolan, released in 2014, there is also an ocean planet, the planet Miller. This watery planet is one of 3 planets orbiting the supermassive black hole, Gargantua. In the movie, the astronauts are tasked with checking to see if any of these 3 planets are habitable. They discover that the planet Miller is under a strong gravitational influence because of its proximity to the black hole, which produces gigantic waves of 1,200 meters or 4,000 feet high. Black holes are very dense regions of space, which contain an immense amount of matter. Their gravitational field is so immense that they absorb all matter, including light. Supermassive black holes have a mass equal to or greater than 1 million times that of the Sun. Beware, Interstellar remains a fiction. According to astrophysicists, a planet in orbit around a supermassive black hole would be uninhabitable. In the case where there would be an accretion phenomenon, that is to say, that the black hole would capture matter with the effect of gravitation, such a planet would be exposed to very hot radiation. It is therefore very unlikely that this planet contains liquid water, and even less likely that it is an ocean planet. In the case where there would be no accretion phenomenon, one could imagine that it is the cosmic microwave background, a radiation emitted 380,000 years after the Big Bang, which would constitute the main source of energy of the planet. According to the principle of relativity, 1 hour on the planet Miller corresponds to 7 years on Earth. This time dilation would allow a planet orbiting a black hole to receive enough heat for liquid water to appear, but the planet would then be too exposed to ultraviolet radiation. Even if it is possible for a planet to orbit a black hole, that world would certainly be very inhospitable. Whether realistic or not, ocean planets fascinate and have fueled the imagination of many science fiction authors and screenwriters. In the early 2000s, Christophe Sotin, a planetary scientist from Nantes, calculated the conditions for the existence of an ocean planet. In other words, he calculated the temperature and pressure conditions under which a planet, which would have been formed at the margins of its solar system, and then would have migrated close to its star, could be covered with water without emerging rocks. The conclusion has delighted science fiction fans. Even if these conditions are locked in relatively narrow limits, they exist. The ocean planet model was initially proposed by the New Zealand astronomer David J. Stevenson of the California Institute of Technology, Caltech, at the turn of the 21st century. This model was then further developed by the team of Christophe Sotin, planetologist and professor at Nantes University. At the origin of the discovery of ocean planets, there is the phenomenon of planetary migration. We speak of planetary migration when a planet moves closer to its star after its formation. This theory was developed to explain the discovery of gas giants too close to their star to have formed there. The first ocean planet was discovered by calculation on December 16, 2009. It was named GJ1214b, or Gliese 1214b, and is located in the constellation of Serpentarius at about 40 light-years from the Sun. We will explore this ocean planet a little later in this trip. But then, how did astronomers come to the conclusion that the ocean planets of science fiction could really exist? Since the middle of the 20th century, even before the discovery of the first exoplanet, important discoveries have been made concerning the presence of water in the universe. In particular, scientists looked at the moons of Jupiter and Saturn. In the 1970s, NASA scientists became interested in Ganymede, a moon of Jupiter, where they suspected the presence of a thick underground ocean sandwiched between two layers of ice. Lewis's work showed in 1971 that radioactive decay could, especially in the presence of ammonia, produce underground oceans in large moons. The search for water on Mars has also been the subject of numerous studies and space missions. Since the first exoplanet was discovered, astronomers are now looking for evidence of liquid water beyond our own solar system. In 2004, Alain Leger, a researcher at the Institute of Space Astrophysics, calculated with his team that a small number of icy planets formed on the outskirts of their star could migrate inwards by up to 1 astronomical unit, the distance between the Earth and the Sun. This migration would melt the ice of the outer layers, forming ocean planets. Today, the existence of ocean planets is no longer a simple scientific hypothesis. Observations from the Hubble telescope, as well as information gathered by space probes such as Galileo, Pioneer, Voyager, or Cassini-Huygens, indicate that several bodies in the universe could harbor liquid water under an insulating shell of ice. But not only. Because the model of the typical ocean planet can vary depending on multiple factors, including the composition of the atmosphere. In June 2020, NASA scientists asserted, based on numerical models, that it is likely that ocean exoplanets are common in the Milky Way galaxy. The first potentially habitable ocean exoplanet was discovered just recently, in June 2022, by the Transiting Exoplanet Survey Satellite. It was named TOI 1452b. Like Gliese 1214b, we will explore it later in this trip. In the meantime, we will discover why ocean planets interest scientists so much. We now know that ocean worlds most certainly exist, even though there is no direct evidence for their existence. Why has this discovery been so important to the scientific community? What is it about these entirely water-covered planets that interests astronomers so much? According to Li Zhang, a researcher at Harvard University, and his team, who classified the exoplanets according to their radius, 1/3 of the known exoplanets are ocean planets. They would thus be billions in the galaxy. and more than a third of the exoplanets discovered would be covered with half water. The Earth is not the only blue planet in the universe. This is good news for astrophysicists who are looking for extraterrestrial life. Astronomers Raphael Luque, a postdoctoral researcher at the University of Chicago, and Enric Palais of the Institute of Astrophysics of the Canary Islands and the University of La Laguna have published an interesting paper in the journal Science. Their study focused on the occurrence of ocean planets around M-type red dwarfs, the most frequent stars in the universe. The conclusion of the study showed that ocean planets are surprisingly frequent around stars of this type. The search for oceanic worlds is important for the search for extraterrestrial life, because water is the origin of life, at least on our planet. This is why NASA is taking a close interest in Europa and Enceladus, icy moons of Jupiter and Saturn. Geysers have been observed on the surface of these moons. The objective of the next exploration missions will be to find molecules of biological origin in the particles spewed by these geysers. It is already known that these two moons have an ocean under an ice pack, and that they are subject to strong tidal forces that cause volcanic activity. This volcanic activity could imply the existence of hydrothermal hotspots at the bottom of these icy oceans. On Earth, these hot springs are home to many forms of life. In the absence of sunlight, it is chemosynthesis that allows living organisms to develop there. Let's look at this in more detail so that you can better understand why, like the icy moons Europa and Enceladus, the ocean planets are of interest to scientists. Water and energy are two essential criteria for the development of life as we know it. Ocean planets already contain water, so it is not surprising that they interest astrophysicists in search of an extraterrestrial life form, especially if these ocean planets are located in the habitable zone of their star, i.e., neither too close nor too far away, so that the temperature, gravity, and pressure conditions are optimal. If it is proven that an ocean planet does contain water in a liquid state, all that remains is to determine a source of energy. The energy released by the planets in the form of heat can come from two sources: the tidal force or the decay of radioactive materials that compose their mantle and crust. The tidal force depends on the elongation of the orbit of the exoplanet. The decay of radioactive materials depends on the mass of its mantle and the age of the planet. Hence the importance, in order to refine the models, of being able to determine with precision the characteristics of the potential oceanic exoplanets observed. And then, is water and energy sufficient for the emergence of life? Planets can evacuate the heat produced by the tidal force or by the decay of radioactive materials via volcanism and tectonics. For a planet to be habitable, it must therefore have volcanic or tectonic activity, but not too much either. Let's get back to Li Zhang and his team. This researcher from Harvard University has used analyses from the European Space Agency's Gaia satellite to develop a new system for classifying exoplanets based on the constant RT for Earth radius. This new model makes it possible to explain the relationship between the mass, the radius, and the composition of exoplanets. a real step forward to better understand their formation and predict ever more accurate models. This new model shows in particular that the formation and the internal structure of planets are constrained by their dimensions. According to the system developed by Gliese and his team, planets with a radius of less than 2 RT are rocky and poor in water. Planets with radius between 2 and 4 RT are water-rich ocean planets. Between 4 and 10 RT, they are planets rich in gas. Beyond a radius of 10 RT, they are gas giants, composed mainly of hydrogen and helium. Gliese and his team have put forward an interesting hypothesis to explain the formation of ocean planets. These planets would have formed like gas giants, but would have eventually evolved differently to become water-rich planets. They are at the limit between a super-Earth and a gas giant, with a mass 8 to 10 times greater than that of the Earth. Ocean planets are numerous, but they are not all habitable. This is where the challenge lies in order not to get lost in endless research. We must know how to distinguish between those that are potentially habitable and those that are not. Ocean planets are interesting for scientists looking for extraterrestrial life, but not only. Even if they are not habitable and do not harbor life, they remain objects to be studied because they provide clues about the formation and evolution of planets, and thus of our solar system. Fasten your seatbelt. We are now going on a journey to the very heart of the ocean planets. What can you expect on this journey? Are the ocean planets similar to Earth? According to studies and models, ocean worlds would not be quite like the Earth, or even like Camino in Star Wars, but rather like the moons of Jupiter and Saturn, Ganymede, Europa, and Enceladus. Let's briefly recall the methods used by scientists to detect exoplanets, and therefore ocean planets. Exoplanets can be detected via the transit method, or via the radial velocity method. The transit method consists in detecting variations in the luminosity of a star when the planet orbiting it passes between the star and the observer. This is called a transit. The transit method allows us to deduce the radius of the exoplanet. The radial velocity method is the one used by the James Webb Telescope. This one embeds a spectrograph, which can highlight a Doppler effect. The Doppler effect is the apparent change in the frequency of a sound or electromagnetic signal from a moving object received by a fixed observer. This method measures the oscillation of a star in response to the gravitation of an exoplanet as the star moves towards or away from us. It works whether there is a transit or not. But if there is a transit, it is always better. This method would then allow us to determine the mass of the exoplanet, its radius, and therefore its density, which allows us to deduce its composition. Valuable information to detect ocean planets. These methods allow us not only to detect exoplanets, but also to know if they are gas giants or rocky planets. The observation of potential ocean planets with these methods has shown us that there would be a typical structure for ocean planets, which would be similar to that of the Jovian satellite Ganymede. Ocean planets would be composed of a core of iron, a mantle of ice and rocks, and a surface ocean, salty or not. How is an ocean planet formed according to scientists' models? Let's go back to the beginning of our solar system to better understand the mechanisms of formation of these aquatic worlds. The formation and evolution of the solar system is described by the model of the solar nebula hypothesis, developed in the 18th century by Immanuel Kant and refined over the centuries. Our solar system would be born from the gravitational collapse of a small part of a nebula. Nebulae are giant molecular clouds. The largest part of the cloud would have formed the Sun, and the scattered remains around the Sun would have formed the protoplanetary disk. This disk, composed of gas and dust, then served as a basis for the formation of planets, moons, and asteroids. In each planetary system, there is what is called the ice line. You may also hear it referred to as the ice line, frost line, or snow line. Whatever you call it, this fictitious line is the boundary between which a given chemical species exists in solid form. In other words, before the line, the species is in the form of gas, and after the line in the form of ice. There is therefore one frost line per chemical species, although this term is generally used to refer to the ice line of water. In the outer solar system, i.e., beyond the planet Mars, planetary objects are born from a structure similar to a comet, i.e., a mixture of water and rocks. They are then less dense than rocky planets. Their composition depends on their position relative to the frost line. Planets and icy moons that form near the frost line contain mainly water and silicates. And planets that form further away may contain, in addition to ammonia, methane, carbon monoxide, nitrogen, and carbon dioxide CO2. As the protoplanetary disk dissipates, the planets that formed further inside the disk will tend to migrate closer to the Sun. Planets that formed in the outer regions and migrated inward are more likely to contain abundant water than planets that formed near the star. A water-rich planet near its star was therefore formed farther away from the star before moving closer to it. The migration of icy planets to the interior of the star system involves the ice melting and becoming liquid, which transforms icy planets into oceanic planets. When a planet forms, much of the water in the planet is initially trapped in the mantle. As the planet cools, the mantle begins to solidify, and large amounts of water, between 60% and 99% of the total amount in the mantle, dissolves to form a vapor atmosphere. This atmosphere can condense to form an ocean. A heat source is therefore necessary to form an ocean. It can be, as you have seen, scientists are trying to establish models of the structure of an ocean planet once it is formed. The structure of an ocean planet depends on many factors and can be inferred from its density, shape, and gravitational pull. Studying an exoplanet can allow scientists to determine whether or not the celestial body has undergone differentiation, that is, separation into rock and ice layers. The small icy moons are made of a layer of water on a silicate core. In the case of Enceladus, the ocean is located between a solid shell of ice on the surface and the silicate core. Since the ocean is in direct contact with the silicates can provide hydrothermal and chemical energy to low-complexity life forms. But Ganymede, which is larger and contains more ice, has an even different and more complex structure. The pressures are high enough that there is an ocean between two ice shells. Imagine a sandwich with the ice instead of bread and the ocean as a filling. The filling of a sandwich is always composed of several elements or layers. This is also the case for Ganymede and the large ocean planets. As the pressure is variable at depth, water worlds may well have a structure that alternates phases of steam, liquid water, high-pressure ice, and plasma. Some of the water contained in ocean planets could take the form of Ice 7, a crystalline form of ice that is stable at high pressure. Let's stop for a minute to think about Ice 7, because it is a fascinating concept. This ice form was modeled by American physicist and Nobel Prize winner Percy Williams Bridgman in 1937. In 2017, it was observed directly in the form of inclusions present in diamonds mined at the Oropa mine in Botswana. These diamonds were formed in the transition zone of the Earth's mantle between 410 and 660 kilometers, or 250 and 410 miles deep, as liquid water subjected to very high pressures and temperatures. When the diamonds were brought up, the liquid water crystallized because of the drop in temperature, the pressure remaining about the same due to the rigidity of the diamond. The ocean of water worlds, thus trapped between two layers of ice, could be maintained if the ratio between the speed of internal heating and the speed of evacuation of the heat is favorable. The heating by the tidal force is thus a criterion of choice in the study of the oceans of these aquatic worlds. The one does not go without the other. Astrophysicists who study ocean worlds must also take into account these characteristics to better understand their structure, since they cannot go there to make direct observations. Smaller ocean planets of less than 1 Earth mass would have, according to the models, a less dense atmosphere and a weaker gravity. Liquid water could thus evaporate more quickly. But liquid oceans could be fed by hydrothermal activity, or tides, for example. Once again, a fragile balance that all potentially aquatic planets may not be able to maintain over time. Let's now move closer to an ocean planet to see what its composition could be. If we take the example of our Earth, water covers 70.8% of the planet's surface, but represents only 0.05% of its mass. The Earth is therefore not what we call an oceanic world. This percentage is much higher in the case of an ocean planet. For example, in the case of TOI 1452b, the first potentially habitable ocean exoplanet discovered in 2022, liquid water would represent 30% of the planet's mass. Does it surprise you that the oceans of oceanic worlds represent such a high fraction of their mass? Actually, it's not that surprising. Models suggest that watery planets have oceans so deep and dense that even at high temperatures, the pressure would turn the water into ice, allowing a mantle of complex ice forms like V-ice to form. V-ice is not necessarily as cold as the ice you know on Earth. Yet another fascinating form of ice. For liquid water on the surface of an ocean planet to remain liquid for long periods of time, the planet must orbit in the habitable zone of its star, also called the Goldilocks zone. its gravitational attraction must be able to maintain sufficient atmospheric pressure to retain the water so that it does not evaporate into space beyond its atmosphere. According to the models, a powerful planetary magnetosphere is needed to protect the atmosphere from mass loss due to stellar winds and to retain the water. Either the atmosphere of a planet is formed by outgassing during the formation of the planet, or it is captured gravitationally from the protoplanetary nebula. It is the greenhouse gases of the atmosphere that will govern the surface temperature of an exoplanet. Greenhouse gases will also absorb and redistribute energy from the star around which the ocean planet orbits, which can give valuable clues about the composition of the atmosphere. The composition of a watery exoplanet and its atmosphere depends, among other things, on its position relative to its star. If the planet is close enough to its star for the liquid water to reach its boiling point, the water would reach a supercritical state. We speak of a supercritical state when water is subjected to high temperatures and pressures, but not to the point of becoming solid. If the ocean planet is colder, then the atmosphere could be much thicker than that of the Earth, and composed largely of water vapor, which could produce a greenhouse effect. The planet would then have to be small enough or close enough to its star for the hydrogen and helium to be volatile. Otherwise, it would be the equivalent of an ice giant, like Uranus and Neptune, but hotter. Icy planets that have migrated to the interior closer to their star could develop thick vaporous atmospheres and thus retain their volatiles for billions of years, even in the event of atmospheric leakage. Atmospheric leakage is caused by ultraviolet radiation and leads to the erosion of the atmosphere, as well as the eventual loss of the oceans. Indeed, atmospheric leakage also means leakage of water vapor, and therefore leakage of hydrogen and oxygen into space. Models estimate that the amount of water lost is roughly proportional to the mass of the planet. You have understood that there is not only one model of atmosphere for the ocean planets. On the contrary, there are many possibilities. However, because a general model must be developed, scientists have estimated that the composition of the atmosphere of an icy planet that became an ocean planet would be about 90% water, 3% ammonia, and 5% carbon dioxide. Now that you have understood how ocean planets are formed and what these watery worlds look like, you are probably wondering if life can develop on them. Can life forms be found on these ocean planets? Or even better, an intelligent extraterrestrial civilization? Are ocean planets inhabited, like the Camino planet from Star Wars? The first thing to know is that if the planet is entirely covered with water on the surface, then the development of terrestrial life seems unlikely. And if there is a layer of solid, pressurized ice between the liquid water and the rocky mantle, the development of life as we know it is even less likely. Scientists have addressed this issue by studying hypothetical ocean worlds. In the case of an ocean planet covered with 5 terrestrial oceans of water, it would not contain enough phosphorus for terrestrial ocean organisms such as plankton to develop. Plankton is an oxygen producer and therefore plays a crucial role in the oceanic ecosystem on Earth. On Earth, phosphorus, which is essential for its development, reaches the oceans through rainwater, that has hit the rocks of the land. A mechanism that could not work on a planet entirely covered by oceans. Another simulation investigated the hypothesis of an ocean world containing 50 terrestrial oceans of water. The pressure on the ocean floor would be so great that there would be no plate tectonics. Without plate tectonics, there is no volcanism. And without volcanism, there is no chemical environment for the development of life as we know it on Earth. However, these observations do not mean that there can be no life on ocean planets. Small ocean worlds like Europa and Enceladus are considered habitable environments because the oceans are in direct contact with the silicate core. Now, the silicate core is a potential source of heat and can also provide chemical elements that could be the origin of life. In addition, according to some researchers, the thick underground ice sheet could be a means of transport for some ingredients of biotic activity. According to a study published in the scientific journal Nature Communications in June 2022, there could be exchanges between the core and the ocean, despite the presence of a thick ice sheet. Until now, scientists thought that this ice, Type 7, was too dense and prevented any contact between the ocean and the core. But finally, this ice is not so impermeable as we thought, and it could bring some chemical elements to the surface. In addition, in 2021, a bioscience study led by Jeffrey Dick and Everett Schock of Arizona State University showed that organisms can thrive on the seafloor without light. This would also be possible on other planets, and thus in ocean worlds. On Earth, life is possible through a mechanism called cellular respiration, which involves the intake of oxygen and the release of carbon dioxide. But this mechanism does not work in the ocean depths without heat or light. This does not mean that there is no life on the seafloor. The study has shown that at the bottom of the oceans there are some specific hydrothermal environments that can harbor complex organisms. This is the case, for example, of hydrothermal vents or hydrothermal mounts, vents located on the axis of oceanic ridges that were formed as a result of tectonic plate movements. Around these vents, hot fluids mix with very cold seawater, an environment that may seem extreme, but is nevertheless conducive to the development and life of tiny organisms. When the vents are composed of ultramafic rocks, magmatic rocks that are very low in silica and produce a lot of hydrogen, this is particularly favorable for the biosynthesis of the basic elements of cells, like amino acids and sugars. Even more energy is needed for a reaction called polymerization, which will create larger molecules such as proteins. This study shows that even in a particularly inhospitable ocean environment, life can be born and develop. This gives hope to scientists who believe that ocean planets could harbor an extraterrestrial life form. If it exists, life on an ocean planet would be very different from life in our terrestrial oceans. For one thing, the oceans themselves would not look anything like our own. The oceans of these aquatic planets would probably be subject to violent storms. Cyclones would form and suck water vapor over the oceans, and since they could not lose their strength over land, they would cause huge waves of several tens of meters high. If there was life in the oceans of the water worlds, then it would have developed rather in the depths, in a calmer zone, or else life would not be easy. Now that you have understood what an ocean planet is, and that you have had a glimpse of what such a planet would look like, we are going to take a trip to the heart of the most famous ocean planets. On this trip, we will go as far as 219 light-years away. You will be able to observe Gliese 1214b, the first ocean planet ever discovered, and TOI 1452b, a potentially habitable ocean planet, discovered in 2022. You'll also see K2-18b, the first exoplanet in the habitable zone where traces of water have been found. And we'll explore multi-planetary systems like TRAPPIST-1, Kepler-62, and Kepler-138, which host several planets, including ocean worlds. Fasten your seatbelt and take off for the watery worlds of our universe. Let's start with Gliese 1214b. This is the first ocean planet that was discovered by calculation on December 16, 2009. This super-Earth, located at 40 light-years from us, is in orbit around the star, Gliese 1214, in the constellation of Serpentarius. Its mass is 5.5 to 7.5 times that of the Earth, and its radius is 2.6 times that of our planet. Its average density is low, 2 grams per cubic centimeter. To give you an idea, the density of the Earth is 5.5 grams per cubic centimeter. This ocean planet would be, according to the estimates, composed to 75% of ice and to 25% of rock and metal. According to this hypothesis, the ocean of ice would be 13,000 kilometers, or 8,000 miles deep, and the rocky core would have a radius of 4,000 kilometers, or 2,500 miles. Close to its star, GJ 1214b would have a surface temperature of about 200 degrees Celsius, or 392 degrees Fahrenheit. Its atmosphere is 200 kilometers, or 125 miles thick, and would favor a greenhouse effect. The presence of life as we know it remains unlikely. Observations of this planet have been made by the Hubble telescope's Wide Field Camera 3, the most advanced instrument on board the telescope to take images in the visible spectrum. According to these observations, Gliese 1214b would be a largely gaseous planet with a high amount of water in its atmosphere. The atmosphere of the planet would be composed of 50 to 85% of water molecules. But how was the presence of water in the atmosphere of Gliese 1214b revealed? In a 2018 study published in the Astrophysical Journal, Japanese scientists demonstrated that the planet's atmosphere did contain water using 2 optical cameras on the Subaru telescope on the island of Hawaii. The scientists waited for the planet to pass in front of its star to analyze the light passing through its atmosphere. For this analysis, they used the phenomenon of Rayleigh scattering, a light scattering phenomenon that occurs when light particles are scattered without a change in wavelength. Installing a blue filter on the cameras of the Subaru telescope made it possible to determine the intensity of the Rayleigh scattering phenomenon. Since the scattering was weak, the scientists concluded that the atmosphere of Gliese 1214b is rich in water. But this conclusion must be refined because a weak Rayleigh scattering can also mean that the atmosphere is dominated by hydrogen and very cloudy. The observations also confirm that this ocean planet was initially formed far from its star, that it was rich in ice, and that it would then have migrated to approach Gliese 1214. Some of the water on this planet could be in the form of hot ice in an exotic state. The exotic state is one of the four possible states of matter, with a gaseous state, the liquid state, and the solid state. Or, water would form a supercritical ocean due to the temperature and pressure conditions. Supercritical water is obtained on Earth by heating water to temperatures above 374 degrees Celsius, or 705 degrees Fahrenheit, under a pressure of more than 221 bar. It is a powerful solvent for all organic compounds. If the oceans of Gliese 1214b were in a supercritical state, life would most likely not be able to develop there. Let's continue our exploration of the exoplanets most likely to be oceanic worlds. Located 100 light-years from Earth in the Dragon constellation, TOI 1452b is the most talked about oceanic exoplanet at the moment because it was discovered just recently, in June 2022. This exoplanet orbits a red dwarf star located in a binary system, which is smaller than the Sun. The two stars of this binary system are separated by 97 astronomical units, which is about 2.5 times the distance between the Sun and Pluto. TOI 1452b can be called a super-Earth because its mass would be equivalent to 4 to 5 times that of the Earth, and it would be 70% larger. TOI 1452b was discovered by an international team led by astronomers from the Université de Montréal. To discover this ocean planet so far from our planet, they used data from NASA's TESS Space Telescope. The main function of the TESS telescope is to observe the celestial vault in search of planetary systems close to our own. To do this, the telescope watches for minute decreases in brightness that are caused by the passage of a planet in front of its star. This passage is called a transit. The analyses of TOI 1452b estimate that 30% of its total mass would be water. The water could be in liquid form on the surface, since the planet orbits in the habitable zone of its star. Observations from the TESS telescope have also shown that TOI 1452b orbits its star in 11 days. To determine the mass of TOI 1452b, scientists observed the binary star system with a Spiru instrument that has been installed on the Canada-France-Hawaii telescope since 2018. The Spiru instrument consists of a high-precision spectropolarimeter and velocimeter and operates in the near-infrared. The objective of this instrument is to locate exoplanets located in the habitable zone of their star, but also to observe the magnetic fields of protostars, i.e., stars that are only a few 100,000 years old. The goal is to finally unravel the mystery of how stars are born. Spiru measures the minute variations in the speed of stars that are caused by the planets orbiting them. With this instrument, researchers were able to estimate the mass of TOI 1452b at about 5 times that of the Earth. According to all the observations that have been made since the discovery of this exoplanet, TOI 1452b, is probably a rocky planet, but with a density much lower than what we expect from a rocky planet like Earth. Observations that make scientists lean in favor of an ocean planet. According to them, TOI 1452b would even be one of the best candidates for the title of ocean planet discovered to date. Separated from the Sun by a relatively short distance on the scale of the universe, 100 light-years, TOI 1452b does not cease to interest astronomers. The James Webb Telescope, launched in December 2021, should help them to establish an even more precise portrait of this ocean planet. Let's continue our journey to the heart of the ocean planets of our universe. Located 40.5 light-years away in the constellation Aquarius, the TRAPPIST-1 system has fascinated astronomers since the discovery of 7 exoplanets around the red dwarf star, TRAPPIST-1a. Not only because 3 of these 7 planets are located in the habitable zone of the star, and are therefore likely to harbor life, but also because such a number of planets in the same system could tell us a lot about the formation of our own solar system. Compared to our solar system, the TRAPPIST-1 planetary system has even more rocky planets in the habitable zone of the star than we do. Our solar system contains 2, Earth and Mars, and TRAPPIST-1 contains 7. The star around which this multiplanetary system is organized is an ultra-cold red dwarf, which is much cooler than the Sun, although it is more massive. It has a diameter of 11.5% that of the Sun, and a mass of 8%. It contains much more metal than the Sun, 109% more, according to scientists, and it can live 400 to 500 times longer, up to 4 to 5 trillion years. TRAPPIST-1a will certainly be one of the last remaining stars when the universe will be so old that the gas necessary for the formation of stars will be exhausted, and that our Sun will have disappeared for a long time. TRAPPIST-1 was discovered in 1999 by astronomer John Gliese and his colleagues. 16 years later, the Belgian telescope TRAPPIST discovered 3 planets orbiting this star. By crossing the information provided by the TRAPPIST telescope and those of other telescopes, 4 other planets were then discovered. These are the planets TRAPPIST-1d and TRAPPIST-1e, which are most likely to contain water in the liquid state, according to astronomers. They are neither the 2 closest nor the 2 farthest from their star. They are in fact the middle planets. TRAPPIST-1b and TRAPPIST-1c are closer to the star, so much so that Planet B orbits TRAPPIST-1a in 1.5 days and Planet C in 2.42 days, or 58 hours. TRAPPIST-1d is the least massive planet of the TRAPPIST-1 system. It has a mass equivalent to 30% that of the Earth. It is also the one which presents the weakest density and the gravity of surface. Its surface temperature is 9 degrees Celsius, or 48 degrees Fahrenheit. To give you an idea, the Earth's surface temperature is 15 degrees Celsius, or 59 degrees Fahrenheit on average. Separated from its star by 2.2% of the distance between the Earth and the Sun, it receives only 4.3% more sunlight than the Earth. TRAPPIST-1d orbits around TRAPPIST-1a in about 97 hours, or a little more than 4 days. Like TRAPPIST-1d, TRAPPIST-1e is located in the habitable zone of the multiplanetary system TRAPPIST-1. This planet has many points in common with the Earth: its mass, its radius, its density, and its surface gravity are approximately similar. The data collected show that its composition should also be similar to that of the Earth. Its average temperature is minus 27.1 degrees Celsius, or minus 16 degrees Fahrenheit, a little colder than Earth's. But since the planet is in synchronous rotation, it would be warmer in the part illuminated by its star, and water would be in liquid state, and on the contrary, colder in the unilluminated part, where it would be in solid state. So yes, the TRAPPIST-1 system has habitable planets, but can we observe ocean planets there? According to a 2018 study by Amy Barr, Vera Dobos, and Laszlo Kiss, TRAPPIST-1d could be covered with an ocean, while the outer planets, i.e. TRAPPIST-1f, G, and H, would be icy planets. However, because we have not been able to observe the TRAPPIST-1 system live, these remain guesses. Other studies show that according to their characteristics, and in particular their atmosphere, other planets of the TRAPPIST-1 system could be watery worlds. The planets F, G, and H could thus have an oceanic surface and a large core. TRAPPIST-1f is probably rocky, with a massive envelope of water vapor at very high pressure and temperature. It could therefore be covered by a thick ocean with an atmosphere rich in abiotic oxygen. Attention, it is not because there would be oxygen that it would be an indication of life. The abiotic oxygen comes in reality from sulfur dioxide. TRAPPIST-1g, the sixth planet of the multiplanetary system, certainly harbors water, since it is less dense but more massive than the Earth. If it has no atmosphere, it is surely an icy planet. But if it has a thick water vapor atmosphere, it could be an ocean planet. As its orbit varies little, it should offer a rather stable climate rather favorable to the development of an aquatic life form. TRAPPIST-1h, the seventh planet of the TRAPPIST-1 planetary system, is even more distant from its star. It could harbor a subsurface oxygen heated by tides. There would thus be on this planet a strong activity of cryovolcanism, with erupting geysers, as on the moons Europa and Enceladus. Let's move a little farther away from Earth to examine a planet called K2-18b, which is located 124 light-years from us in the constellation Leo. This planet, discovered by the Kepler Space Observatory in 2015, orbits the red dwarf star K2-18 in 33 days and is located in its habitable zone. However, scientists believe it is unlikely to be habitable. K2-18b is 8 times more massive than the Earth. It is a super-Earth or mini-Neptune. In 2019, 2 independent studies concluded by cross-referencing data from the Kepler, Spitzer, and Hubble space telescopes that the atmosphere of this planet would contain significant amounts of water vapor. The equilibrium temperature of the planet is estimated to be about -8 degrees Celsius, or 17 degrees Fahrenheit, and it receives 94% of the stellar illumination that the Earth receives. Based on its size and density, it is unlikely to be composed entirely of iron and silicates, so it could be composed of hydrogen, helium, and ice water. In 2019, analyses of Hubble data by researchers from the University of Montreal and University College London examined the spectra of starlight passing through the planet's atmosphere during transits and concluded that K2-18b has a hydrogen-helium atmosphere with a high concentration of water vapor, between 20 and 50%. The water vapor could be high enough to form clouds. K2-18b was the first super-Earth discovered in the habitable zone of a star with a detected atmosphere. It was also the first discovery of water in an exoplanet located in the habitable zone. As a result of these observations, scenarios have been developed to determine possible models for this exoplanet. Several of these models admit that K2-18b could be an ocean world covered with liquid water and with temperature and pressure conditions similar to Earth. We will know more with the observations of the James Webb Telescope, launched at the end of 2021, and the Space Telescope Ariel, developed by the European Space Agency, which should be launched in 2028. The star Kepler-62 is much more distant than TRAPPIST-1 or even K2-18b. Located in the constellation Lyra, 1,200 light-years from Earth, it is an orange dwarf. At least 5 planets orbit it, including Kepler-62 and F, which are located in the star's habitable zone. In 2013, when they were discovered by the NASA Kepler Space Telescope, they were called the 2 most Earth-like planets ever discovered. Kepler-62e is a super-Earth, telluric like Earth, with a composition of iron and silicates. According to the hypothesis of scientists considered the most probable, it would contain an abundant quantity of water, in addition to its rocky core. According to a modeling study of this planet, published in the Astrophysical Journal, it is likely that the planet is entirely covered by an ocean. Kepler-62f is the farthest planet from the star Kepler-62, so it is located in the outer part of its habitable zone. It is 1.4 times larger than the Earth, so it is also a super-Earth. It receives as much solar energy as Mars, and the year lasts 262 days on this planet. Like Kepler-62e, it would be one of the first 2 viable candidate planets as a habitable zone ocean planet. A University of California study led by astrophysicist Omawa Shields and published in 2016, estimated that the temperature of this planet would be compatible with the presence of liquid water. However, for Kepler-62f to indeed harbor oceans, it must meet a few criteria. The planet would have to have an atmosphere 3 to 5 times thicker than Earth's, because its star heats less. This atmosphere, to maintain a temperature allowing the presence of water in a liquid state, should be composed largely of CO2. If, for example, the planet had an intense volcanic activity, it could maintain an atmosphere rich in carbon dioxide. And for it to be habitable, its atmosphere would have to be 3 to 5 times thicker than that of the Earth, as we have just seen. And in addition, the level of CO2 would have to be 2,500 times higher. What about the other planets in the Kepler-62 system? Astrophysicists have discovered 2 ocean planets, so they did not stop there. They investigated whether the other planets orbiting Kepler-62 could also be water worlds. Kepler-62b is the innermost planet in the multiplanetary system. It is about 30% larger in diameter than Earth and has an equilibrium temperature of 477 degrees Celsius or 890 degrees Fahrenheit, which is slightly higher than that of Venus. No doubt, it is not an ocean planet. Kepler-62c is the second innermost planet after planet B. It is about the size of Mars, but looks more like Mercury, the closest planet to the Sun in our solar system. It is therefore unlikely that this planet contains liquid water. Finally, Kepler-62d is not yet in the habitable zone, so it is too close to its star for water to remain in a liquid state. We end this journey with the planetary system Kepler-138. The star Kepler-138, or KOI 314, is a red dwarf star located in the Lyra constellation, 219 light-years from Earth. It is in the field of view of NASA's Kepler spacecraft, hence its name. In orbit around this star, 3 planets have been confirmed, and a 4th planet is likely. Kepler-138b is among the exoplanets whose size and mass have been measured, the one with the lowest mass. To give you an idea, the mass of Kepler-138b is similar to that of Mars. As for Kepler-138d, it has a very low density, so much so that it was long thought to be a gas dwarf planet, or mini-Neptune. A mini-Neptune is a planet whose mass is significantly less than that of Neptune, but which still shares some commonalities with this planet of our solar system. Mini-Neptunes have a thick atmosphere of hydrogen and helium over a deep mantle of water, ammonia, and other volatile compounds. If they did not have such a thick atmosphere, mini-Neptunes would actually be ocean planets. Recent studies from 2022 have shown that Kepler-138c and Kepler-138d are certainly watery worlds, with oceans 500 times deeper than those of Earth. They would also be warmer, with an atmosphere of hot water vapor. Let's go back for a moment to December 2022. Astronomers announced that they had identified the first true ocean planets, Kepler-138c and Kepler-138d. To reach this conclusion, astrophysicists compared the densities and masses of these planets with existing models. And indeed, while these 2 planets are larger than the Earth, their density is nevertheless located between that of a rocky planet and that of a gas giant. To identify these oceanic worlds, astronomers used data from the Hubble and Spitzer space telescopes. The depth of the oceans of these 2 watery planets would be 500 times higher than the average of the terrestrial oceans, that is to say, a depth of at least 1,600 kilometers or 995 miles. Astrophysicists compared these 2 planets to Europa and Enceladus, except that Kepler-138c and Kepler-138d are larger and hotter than these oceanic moons. And instead of an icy surface, there would be large envelopes of water vapor. Kepler-138c and Kepler-138d constitute for astrophysicists the best evidence to date of the reality of oceanic planets, whose existence was theorized a long time ago. The oceans of these two planets would, however, be different from our terrestrial oceans. The available data show that they would be significantly warmer than our oceans, and that they would be under higher pressure. There may also be no clear boundary between the surface of the oceans and the atmosphere of Kepler-138c and Kepler-138d, which is certainly hot and composed of vapor. The temperature of this atmosphere is certainly above the boiling point of water. Under this hot atmosphere, there could be liquid water at high pressure, at depth, or in another phase like supercritical water. We have arrived at the end of this journey to the heart of the mysterious ocean planets. These aquatic worlds seem to come straight out of the imagination of a science fiction author. And yet, astrophysicists believe that it is more than likely that they really exist. What kind of creatures inhabit these extraterrestrial oceans? Are they microorganisms invisible to the naked eye? Huge prehistoric-looking creatures? Or ferocious creatures, like the Kraken of the fictional planet Mon Cala? Do these aquatic creatures have, as in our terrestrial oceans, a language to communicate between them? Do they inhabit the abysses of oceans more than 1,600 kilometers or more than 1,000 miles deep? Astrobiologists, astrophysicists, and astronomers are asking these questions and hope one day to be able to provide answers. The planet Earth was formed within the solar system. This solar system is a precious territory, more than 4 billion years old, and includes the Sun, the 8 known planets, as well as many small bodies of rock and ice, called asteroids and comets. The solar system is divided into several zones. The inner zone consists of the so-called telluric planets, Mercury, Venus, Mars, and of course the Earth. These 4 planets are rocky and metallic. Their size is relatively small. During their formation, the heat of the Sun has driven the gases from this area to concentrate dense elements. Beyond Mars, there is a belt of asteroids. These are millions of blocks of rock, waste products of the formation of planets. From this asteroid belt, we enter the domain of the giant planets, Jupiter, Saturn, Uranus, and Neptune. In this external zone of the solar system, the lower temperature during the formation of our solar system allowed the existence of volatile elements. The planets are larger in size than the terrestrial planets and are composed of light elements such as hydrogen and helium. The formation of the solar system took place after a nebula gradually collapsed on itself, following the explosion of a supernova. The primitive nebula flattened under the effect of its rotation. The central part of the nebula heated up and formed a protosun. Dust rich in carbon, ice, metals, and minerals have then clumped together. This phenomenon is called accretion. These blocks met until they formed protoplanets, and then a few million years later, the planets in their current size. If we start from the Sun, the Earth is the planet that is in 3rd position. It is the only planet in the solar system with liquid water on its surface. 70% of the globe is covered with oceans several tens of kilometers deep. Its atmosphere is composed mainly of nitrogen and oxygen. The conditions found on this terrestrial planet have allowed life to develop and evolve in a complex manner. Currently, no other planet is known to harbor life. The Earth has always been subject to vigorous volcanic activity. It has a diameter of almost 13,000 kilometers, or about 8,000 miles. The Earth has a very particular composition, since to date is the only telluric planet that has 4 distinct layers, including a core in 2 parts. On the outside, the Earth's crust is 5 to 80 kilometers, or 3 to 50 miles thick. It is mostly composed of rocks derived from volcanism. Under the crust is the mantle. Although it is hot and malleable, it remains solid and extends to almost 3,000 kilometers, or 1,900 miles deep. It is composed of minerals such as oxygen, silicon, iron, and magnesium. At the center of the Earth is the core, which is divided into 2 parts. The outer core is composed of metallic elements. Its liquid structure is traversed by electric currents that create the magnetic field. The solid inner core, composed of iron and nickel, is subject to a phenomenal pressure and a temperature reaching 6,000 degrees Celsius, or 10,800 degrees Fahrenheit. The Earth's atmosphere contains very little carbon dioxide because it dissolves in the oceans. Nitrogen dominates our atmosphere, followed by oxygen, argon, some other gases, and water vapor. The gases present are transparent, whereas water vapor is visible when it condenses into a cloud. The latter can cover up to 60% of the Earth's surface. In the solar system, the atmosphere most similar to that of the Earth is that of Titan, a moon of Saturn. The atmosphere of Mars is 100 times less dense than that of the Earth, and that of Venus is 100 times more dense. Ozone is a molecule that contains 3 oxygen atoms. The gas present in the atmosphere absorbs the harmful ultraviolet rays of the sun, allowing life to thrive on the surface. The Earth is different from other planets because of its geology and its complex climate. Another of its characteristics is that its crust is divided into tectonic plates that are mobile in relation to each other. The other telluric planets are called monoplate because they have only one crust. This division of the crust into tectonic plates gives rise to telluric movements. If seen from the sky, the Earth looks like a blue planet, it is because 2/3 of its surface is covered by oceans, and that erosion has erased the craters of asteroids and comets that may have hit its surface. Next to the Earth is the Moon, its satellite. It is the 5th largest satellite and the only moon in the solar system to be called Moon. The Moon is devoid of atmosphere and life. There has never been liquid water on the Moon. Meteorite impact craters and ancient volcanic eruptions shape its surface. Seen from Earth, the Moon offers 2 types of very contrasting terrain, with dark and light areas. The latter, called continents, are massive areas riddled with asteroid impact craters that formed in the first billion years of the solar system's history. The dark areas are called seas. They are vast plains of lava emitted by volcanoes. The Moon exerts a significant attraction on the Earth, although it has a weak gravity field and is rather far from the planet. Combined with the attraction of the Sun, the influence of the Moon causes the tides, which result in the rise and fall of the waters of the oceans. During a full or new moon, when the Moon, the Earth, and the Sun are aligned, the forces of gravity add up to create the high tides. The high tides are then very high, and the low tides very low. When only a quarter moon appears, the Earth to Moon and Earth to Sun axes are at right angles, and the forces of gravity partially cancel each other out. The tides, called neap tides, are then reduced. The one who reigns supreme in this gigantic domain, and without whom the Earth, and consequently man, would be nothing, is the Sun. This giant ball of hydrogen and helium contains 99.9% of the total mass of the solar system. The Sun is a star. Although it seems huge to us, it is medium-sized with a diameter of almost 1,400,000 kilometers, or 870,000 miles. The Sun is in the middle of its life cycle, since it has already used up between 35 and 45% of its hydrogen reserves. In about 6 billion years, the hydrogen will be totally consumed, and the Sun will start to expand. It will then become a subgiant star, brighter but less hot. A billion years later, the star will become a red giant, growing even larger. It will then eject its outer layers into space until its core curls up into a white dwarf. It is within its core, the central region of the Sun, that nuclear reactions occur. The energy released rises to the surface and escapes in the form of light and radiation. It is thanks to this same energy that life on Earth is possible. The atmosphere acts as a shield. It allows the solar energy to penetrate and prevents the heat from escaping, while preventing the dangerous solar radiation from reaching the planet. This effect is called the greenhouse effect. The atmosphere keeps us comfortably warm day and night. Human beings are entirely dependent on the Sun, which is involved in the entire life cycle. The star heats the land, oceans, and air. When the water evaporates, clouds form. Within these clouds, water droplets are formed as the water vapor cools. They will then fall back down as rain. Humans, animals, and plants benefit from this water. Plants also use sunlight for photosynthesis. They convert carbon dioxide and water into carbohydrates necessary for their development. In return, they release the oxygen that living things need to breathe. Mercury is the closest planet to the Sun. It looks like a ball of iron surrounded by a thin rocky mantle. Its surface is, like that of the Moon, covered with impact craters. The Caloris Basin is one of the best-known impacts, so large that it could contain almost the whole of Texas. Apart from the craters and plains, compression faults appear, which form cliffs, and which can reach 3 kilometers or 2 miles in height. Having no atmosphere or liquid water, Mercury's only erosion comes from the impact of meteorites, asteroids, and comets. Mercury has no moon. Its proximity to the Sun results in an average ground temperature of 430 degrees Celsius, or 800 degrees Fahrenheit. It also experiences great temperature contrasts, since when its hemisphere is plunged into the night, the temperature decreases to about minus 200 degrees Celsius, or minus 328 degrees Fahrenheit. It is smaller than the Earth, but so dense that it certainly has an important iron core. Venus is the closest planet to Earth. It is about the same size as Earth, but is far from being its twin. A thick atmosphere of carbon dioxide covered with clouds of sulfuric acid obscures its surface. The pressure exerted on the ground is equivalent to that of a deep sea of 900 meters or 3,000 feet. While it is farther from the Sun than Mercury, the average ground temperature of Venus is warmer and reaches up to 490 degrees Celsius, or 914 degrees Fahrenheit. The surface of Venus is covered with volcanic edifices such as pancake domes, which are circular and flattened reliefs formed by a gas-rich lava. This lava spreads like a pancake batter, then solidifies and breaks. The highest volcano on Venus is Mont Mons, which rises to 8,000 meters or 26,000 feet. Its lava flows can reach hundreds of miles and miles in length. Mars comes in fourth from the Sun. Its diameter of just over 6,700 kilometers or 4,200 miles is twice as small as Earth's. It has a thin atmosphere containing mainly carbon dioxide. Its unstable climate leads to the formation of ice caps. Many extinct volcanoes culminate on its surface, including Olympus Mons. It is one of the highest known landforms in the solar system, with a peak reaching over 21,000 meters, or 69,000 feet. It seems that liquid water, in the form of real seas, covered its surface in the distant past. The first geological hours of Mars were marked by meteoric bombardment and strong volcanism. The ancient craters thus eroded by water gave birth to rivers. There was then at that time a hydrodynamic cycle. The climate should be mild and stable, thanks to the presence of oceans allowing the water cycle. Nevertheless, the weak mass of the planet could not allow to retain the gases of its atmosphere, and the cycle of the water dissipated. The water would then have evaporated and been absorbed within porous rocks. The density of Mars is lower than that of the Earth, because its smaller mass compresses its deep layers less. It is called a red planet because of a thin layer of red dust composed of iron oxide that covers its surface. Most of the southern hemisphere is covered by high plateaus riddled with impact craters. In the north, there are basins and large volcanoes. Mars has two moons, Phobos and Deimos. These are asteroids that have been captured by its gravity field. They are riddled with craters and have irregular shapes. Both are small, with modest diameters of 27 kilometers or 17 miles for Phobos, and 15 kilometers or 9 miles for Deimos. The distance between Deimos and Mars is such that it is in synchronous orbit with the planet. The Moon is always at the vertical of the same place. A cluster of asteroids circulates between the orbits of Mars and Jupiter. Irregularly shaped, they can reach sizes ranging from a small stone to a mini planet. The largest of them, Ceres, has a diameter of about 950 kilometers or 590 miles. It was even classified as a dwarf planet. Asteroids are composed of minerals, metal, or carbon. They are riddled with impact craters. They could not aggregate to form a planet because the gravity field of Jupiter disrupted and scattered the blocks. These rocky bodies orbit the Sun, but their small size prevents them from being classified as planets. The majority of asteroids are located in the main belt. Its thickness measures between 100 and 300 million kilometers, or between 60 and 190 million miles. Asteroids are classified into 3 distinct families according to their chemical composition and morphological characteristics. We find the asteroids of type C, called carbonaceous, the asteroids of type S, rich in silica, and the asteroids of type M, said metallic. About 75% of them are C-type asteroids.
They are lodged in the most distant regions of the asteroid belt and are the least luminous. Can these lumps floating in the sky be made to crash into the Earth and become a threat to life? Some fragments of asteroids can head towards the Earth and collide with it. They are called meteoroids. If one of these meteoroids enters the Earth's atmosphere at high speed, the friction creates heat so great that it burns the meteoroid to ashes and produces a trail of light across the sky. If the meteoroid does not burn up completely, the remaining piece can then touch the Earth. It is then called a meteorite. An impact with a large meteorite could obviously leave obvious signs on the surface of the Earth and cause dramatic consequences for life. Jupiter is the largest planet in the solar system. It could contain all the other planets in its interior. Its composition is almost entirely gaseous and consists mainly of hydrogen and helium. Jupiter is more like a star than a real planet. After Venus, Jupiter is the most luminous planet. It has a compact core of rock and ice, formed of compressed hydrogen and helium. This core represents about 5% of its mass. It is enveloped by volatile elements. Jupiter is spectacular. It has no solid surface and a dynamic atmosphere. From the Earth, we can observe an alternation of dark belts and clear areas. This banded arrangement is due to its rapid rotation, which stretches the disturbances around the globe and confines the clouds of its atmosphere in a set of parallel lines. In the middle of these bands, cyclones and anticyclones are present. The most famous of them is the Great Red Spot. It owes its bright color to molecules containing phosphorus. This anticyclone is larger than the Earth. The Great Red Spot is constantly shrinking from 40,000 kilometers, or 25,000 miles, in 1930 to 16,000 kilometers, or 10,000 miles long, in 2014, and would disappear within 70 years. Jupiter has a ring system that remains dark and is only visible when it is in the planet's shadow. The planet is not only distinguished by its size, it also has the largest number of moons. To date, 95 are known. Saturn is the second largest planet in the solar system. But what makes it famous are the rings that surround it. With the help of a small amateur telescope, it is possible to observe them from Earth. Saturn's rings are a world apart. They are composed of many ice particles acting as an independent satellite. Some of them can reach the size of a house. The particles in these rings are shiny, coated, or composed of highly reflective ice. Saturn's rings are brighter than those of other planets and reflect up to 60% of sunlight. They are flattened. Although they measure 280,000 kilometers, or 170,000 miles in diameter, their thickness does not exceed a few meters or feet on average. Saturn has a solid core of rock and ice. Its atmosphere contains mainly hydrogen and helium. The clouds are deeply buried, and their color, blurred by layers of haze, gives the planet a livid hue. One of the characteristics of Saturn is that it has a flattened shape at the pole. This is due to its extremely fast rotation on itself, of less than 10 hours 30 for a complete turn. Saturn, imposing in terms of mass and gravity field, has captured a large number of asteroids that have become its moons. 83 known satellites are attributed to it today. Among them, Titan has a diameter of more than 5,000 kilometers, or 3,100 miles, and is the second largest moon in the solar system. Titan is surrounded by a thick layer of nitrogen. Being quite far from the Sun, the temperature on its surface is extremely low. By continuing to move away from the Sun, we can observe in the sky a ball with blue-green reflections. It is the planet Uranus. It is the third largest planet. Its diameter is 4 times that of the Earth. Its particular color is due to the presence of methane. No details of its atmosphere are visible, neither cloud bands nor cyclonic formations. Unlike Jupiter and Saturn, which are considered as gas giants, Uranus is similar to an ice giant. It is much denser, and its internal layers must contain elements heavier than hydrogen, like ice. Uranus goes around the Sun in a little more than 84 years. This situation gives it strange seasons. This is also explained by the fact that its rotation axis is almost lying in the plane of its orbit. Long periods of sunlight follow long periods of darkness. During the winter solstice, the northern hemisphere is plunged in the night for 21 years. The planet Uranus has rings. 13 are currently known, 11 located in the inner system and 2 in the outer system. Their capacity to reflect light is extremely low. They are therefore difficult to see. These rings are composed of dust particles with dimensions of the order of a centimeter. They could have been formed by the fragmentation of a small moon after a collision with a meteorite. Uranus has so far 27 known moons. 5 of them are large. The others are only a few tens of kilometers in diameter. The largest, Titania, measures 1,580 kilometers in diameter. But the strangest of the moons encountered so far is Miranda, the 5th satellite of Uranus in size. Its surface shows complex and extraordinary geological formations. One could compare it to a giant puzzle, as if this moon had been torn apart and then put back together. It could be that Miranda was smashed during a collision, and that the pieces in orbit around Uranus were then reassembled until the moon was reconstituted. Neptune is a gas planet. Unlike Jupiter and Saturn, its solid core is larger than its total mass. Neptune's atmosphere is characterized by strong winds of over 2,000 kilometers per hour, or 1,200 miles per hour, and large cyclonic formations that persist for long periods. The most visible large dark spot is as large as the Earth. The last planet in the solar system glows with a beautiful azure color. This hue is explained by the presence of methane in its atmosphere, which absorbs red radiation and lets only blue radiation filter through. Its atmosphere is composed, in addition to methane, of hydrogen and helium. Neptune has an important internal heat source, since it emits a quantity of energy equivalent to almost 3 times that received from the Sun. 5 rings surround Neptune. They are composed of ice, covered with a large carbonaceous dust, and remain very difficult to detect. Because of its remote distance from the Sun, the number of Neptune's moons remains poorly known. Triton is the largest of Neptune's satellites known to date. This moon has canyons, craters, peaks, and very long fissures, forming a most amazing landscape. It also has very strange volcanoes on its surface. It seems that Triton's volcanoes look like geysers that emit jets of gas and dark carbon compounds from underground. Pluto was considered the 9th planet in the solar system. In 2006, it was reclassified as a dwarf planet. Dwarf planets are considered to be stars orbiting a star, more or less spherical, and often found in the vicinity of many other large objects such as asteroids, comets, or other dwarf planets. As their name indicates, these planets are small. They cannot exert the gravitational forces necessary to attract and hold objects in their orbit. With its 2,300 kilometers, or 1,430 miles in diameter, Pluto is smaller than the Moon, and yet the largest and second most massive dwarf planet. Its essentially rocky core occupies the majority of the planet's volume. Its surface consists of plains and mountains, covered with a thick layer of ice, probably water, mixed with traces of methane, nitrogen, and carbon monoxide. It takes almost 250 years for Pluto to go around the Sun. Beyond Pluto, a vast region of comets opens up. Comets are visible to us as they approach the Sun, as they develop a glowing tail. But billions of invisible comets stay at the edge of the solar system. Comets are classified into two families: long-period comets that circle the Sun in more than 200 years, and short-period comets. The long-period comets have orbits inclined with respect to the circulation plane of the planets. Their trajectories are varied, suggesting that they belong to a vast spherical cloud that envelops the solar system like a cocoon. The Kuiper belt is the source of short-period comets. It is located around 30 astronomical units and extends to hundreds of astronomical units. It is home to hundreds of icy objects, some of which reach the size of large asteroids. Extending over a few tens of billions of kilometers, it is 1,000 times smaller than the Oort cloud. The Oort cloud is the reservoir of long-period comets. It extends over distances between 30,000 and 100,000 astronomical units. This spherical cloud is hypothetical, since it could not be observed directly, as it is beyond the reach of our instruments. The knowledge of its existence is based on the analysis of the orbits of several comets. In 1932, the first astronomer postulated that comets orbiting for long periods of time came from a large cloud located beyond the limits of the solar system. About 20 years later, another astronomer put forward a theory according to which meteorites could not have formed in their current orbit because of the astronomical phenomena that govern them. He deduced that they must be stored in a large cloud, the Oort cloud. A comet that passes near the Sun loses part of its mass, volatilized into gas and dust. One might think that in a few tens of thousands of years, a comet should have completely melted. However, the solar system has always been full of comets. There is, in fact, a vast reservoir of comets hibernating around the Sun. As the Sun moves through the Milky Way, it is subject to tidal forces as it passes near other stars. Comets can then be dislodged from the Oort cloud and directed towards the interior of the solar system. Comets are bodies composed of a head, which includes a nucleus surrounded by a luminous hair of gas. The nucleus of the comet presents different colorations, varying from black to gray through red. The nucleus is composed of common silicate and molecules composed of carbon, oxygen, nitrogen, and hydrogen. When it is far from the Sun, the comet is invisible, like many other small celestial bodies. As the comet approaches the inner regions of the solar system, the heat produced sublimates some of the ice present in the nucleus gas, which, mixed with other gases, forms the hair and the tail. As the comet passes through the solar system, the material of which the short-period comet is composed is depleted and transforms it into a tiny body among others. It happens that the Earth, during its own rotation around the Sun, crosses the dust or gases that have been left behind by a comet. These materials, while crossing our atmosphere, create magnificent swarms of meteors that are called shooting stars. During the formation of the comet's hair, carbon dioxide and carbon monoxide first evaporate. Then it is the turn of the ice. The emitted gas disperses in space and is replaced by new matter. The vaporization takes place only on the side facing the Sun, where the comet is active. The material emitted from the nucleus can spread out into space for hundreds of thousands of miles and miles. When the comet shines and becomes visible, its tail can be seen, which comes from the gases in the hair. A comet has in most cases at least two tails. One is composed of ionized gas and the other of dust. The latter are not always visible. The gas tail is bluish in color because of the presence of carbon monoxide. It can measure up to several 100 million kilometers and miles. They are always straight and consist of structure, node, and condensation. The sudden separation of the tail from its hair is one of the most spectacular phenomena. Man, from his planet Earth, seems infinitely small when placed on the scale of the solar system, and yet the universe is far from stopping there. The solar system is located in a galaxy called the Milky Way. It is a huge disk of stars in motion that measures nearly 1,000 million billion kilometers in diameter. Along its diameter, one could line up 130 million solar systems. And yet, the Milky Way is one galaxy among many. Galaxies are gigantic clusters of stars that can extend over hundreds of thousands of light years. Presenting a wide variety of sizes and shapes, galaxies are classified into two main families: elliptical and spiral galaxies. Spiral galaxies are further subdivided into simple spiral, barred spiral, and lenticular galaxies. Elliptical galaxies are the most massive. The spiral and lenticular galaxies can reach diameters similar to the large elliptical, but are less massive because they are flattened. Spiral galaxies represent 60% of all cases, and 30% are elliptical. The best known remain the spiral galaxies. Among them, we find barred spiral galaxies, which have a thick bar of stars crossing their heart and extending by an arm at each end, and normal spiral galaxies, which see their arms emerging directly from the heart of the galaxy. Spiral galaxies are flattened like a disk, with a central bulge of old red stars. The disk at the periphery contains clouds of gas and dust that will serve to form new stars. Spiral galaxies are rotating, resulting in density waves that compress the gas and dust to form bright blue stars that illuminate their arms. A spherical halo of globular clusters, containing up to 1 million old red stars, surrounds spiral galaxies. The so-called elliptical galaxies have a slightly flattened oval shape. They have 3 axes of different lengths. The lenticular galaxies have, as for them, a lens shape. They remind both spiral galaxies and elliptical galaxies. They have, like spiral galaxies, a disk with a central bulge that houses clouds of gas and dust. They differ by the absence of spiral structure. They do not have young blue stars and host only old red stars. There are two theories explaining how galaxies are formed. According to the first theory, galaxies form from huge clouds of gas that collapsed in on themselves by gravity. The second theory suggests that galaxies would have assembled from smaller objects. Both processes could have been at work when the galaxies formed more than 10 billion years ago. Just 1 or 2 billion years after the Big Bang, the universe then consisted of a vast expanse of hydrogen and helium. Some parts of this universe, denser than others, attracted matter, thanks to their gravitational forces. These regions individualized into huge clouds that would later become future galaxies. These different clouds were brought to meet and thus form even denser sets. During the collisions, shock waves stirred up the gas and caused it to collapse into stars and star clusters. It seems that in earlier times, the universe contained a higher proportion of spiral galaxies than today. This change in the appearance of the universe is due to repeated collisions between galaxies. Indeed, when spiral galaxies collide, they merge to give elliptical galaxies. The merger thus explains their large size and why they contain so little gas and so many red stars. From our human eyes in the night sky, the Milky Way appears as a whitish molten band crossing the celestial sphere. It takes the form of a ring, of which only a part is revealed. From the Earth, its brightness is weak and diffuse. In reality, we can only see the side of the galactic disk, composed of an endless string of stars that the human eye is unable to distinguish. Many stars, planets, and nebulae populate the Milky Way. A star is a ball of ionized gas made up primarily of hydrogen and helium, the two most abundant elements in the universe. Stars tend to collapse under their own weight. This is called gravitational contraction. The nuclear reactions that occur within the star also exert pressure from the inside out. The balance between these two forces gives stars their own dimension. The core of the star is subjected to high temperature and pressure. The hydrogen nuclei collide and form helium nuclei. Thanks to these reactions, a star can shine for billions of years. Its surface temperature will depend on its color. Our Sun is a yellow star of average size. Stars are born in molecular clouds. These are large areas of gas inside which some regions are denser than others and attract by gravity the gases present around. A globule is then formed and contracts until it becomes a protostar. The contraction causes an increase of the rotation, as well as an increase of the temperature and the pressure. The thermonuclear reactions start. The star is born. The north and south celestial poles are the extension of the Earth's axis to infinity and are the only two immobile points in the sky. The North Star indicates almost exactly the North Pole. It is not very bright, since it is only the 48th star in the sky in order of brightness, but it is one of the most important landmarks since it does not move and always indicates north. Thanks to it, it is possible for us to orient ourselves at night from Earth without a compass or GPS. 200 billion stars populate the Milky Way, and only 3,000 of them are visible to the naked eye. The closest star system to us is Alpha Centauri. It is a complex system composed of 3 stars. The 2 largest form a double star, located 4.37 light-years from the solar system. Their size and color resemble those of the Sun. They are accompanied by Proxima Centauri. It is a tiny star, a brown dwarf, measuring 1.5 times the size of Jupiter. Proxima Centauri is a little closer to us than the main components of Alpha Centauri, since it is 4.24 light-years away. From Earth, Alpha Centauri shines with an impressive brightness. It is the 3rd brightest star in the sky. With the help of a telescope, the 2 main components of Alpha Centauri form a beautiful double star. Several types of stars populate the Milky Way: binaries, multiples, and variables. Almost half of the stars in our galaxy are binaries. Binary and multiple stars are stars that orbit a common center of gravity and are bound together by gravitational attraction. Binary stars form within the same cloud of matter, which during its collapse splits into 2 pockets. Some clouds split into multiple parts and can group up to 6 stars. A variable star sees its brightness change for several reasons. When a star passes in front of another, for example, it will modulate the amount of light we receive. The periodic pulsations of the star's surface can also change its brightness. The light emitted is a function of the surface of the star. Stars at the end of their life expand and contract. Stars can undergo unpredictable variations in brightness due to gas eruptions or other cataclysmic phenomena. Chelyabinsk is an eclipsing binary star, which is very surprising. It consists of 2 stars so close to each other that they exchange matter and deform each other. The larger of the 2 loses the equivalent of the mass of the Sun every 50,000 years. Chelyabinsk is located in the constellation of Lyra. If our planet were positioned near this infernal stellar couple, the inhabitants would see huge protuberances tear away from the larger one to wrap around the smaller one. But from the Earth, we only notice the brightness of Chelyabinsk diminished as soon as the smaller star passes in front of the larger one. A set of neighboring stars can sometimes present a figure on the celestial sphere. These are the constellations. From the Earth, man can observe different figures drawn by stars like Orion, the Big Dipper, or the Southern Cross. The stars have their own movement, but they are so far away from us that they seem fixed. Their position will change gradually to the point that our familiar constellations will become totally unrecognizable in the distant future. The Big Dipper is the most famous constellation in the Northern Hemisphere. It is close enough to the celestial pole, where the North Star is located, that it never disappears below the horizon, whatever the time of night or the season. The 7 brightest stars of the Big Dipper form a distinctive saucepan shape. Most of its stars are less than 100 light-years away and belong to an open cluster that is almost completely dislocated. Many legends have been associated with this constellation. According to Greek mythology, it represents the nymph Callisto, changed into a bear by Hera, the wife of Zeus, after her husband fell in love with her. Zeus would then have raised the bear to the heavens to place it near the sun, Arcus, whom he had with Callisto, and who is also transformed into a little bear. The universe favoring groupings, the stars are often binary or multiple. But on a larger scale, larger groupings of stars are formed as open or globular star clusters. Globular clusters can contain from 100,000 to more than 1 million stars. They are similar to tiny elliptical galaxies. They contain old stars of red color, while the open clusters are populated by young blue stars. Within these clusters, collisions are frequent, leading to the formation of new stars called blue wanderers. Globular clusters orbit the center of the galaxy, and together form a spherical halo. The Milky Way contains nearly 150 globular clusters in its halo. One of the brightest clusters is Omega of the Centaurus. It peaks high in the southern sky in March and April. To the naked eye, it looks more like a spot than a star. Through a telescope, we can see that many small stars dot its surface. Omega Centauri contains nearly 10 million stars over 10 billion years old. It is the largest globular cluster in the galaxy. This cluster could be the remnant of a small galaxy that was swallowed by our Milky Way. Nebulae are interstellar clouds that contain the raw material to make new stars. These clouds come in a variety of sizes and colors. The smallest nebulae are called globules. Their diameter is of the order of a light year, and they look like dense and dark spots. Large molecular clouds contain enough material to make tens of millions of stars. All clouds are composed of gas and helium, as well as grains of carbon and silicon dust. When a new star forms in an interstellar cloud, the light ionizes the gases and creates luminescence. Some clouds do not emit their own light. They reflect or scatter the light of nearby stars and nebulae. The Orion Nebula is the closest to Earth. It shines according to a phenomenon of fluorescence. The atoms of the gas are stimulated by the ultraviolet radiation of bright stars, which leads them to diffuse light in turn. In this nebula, many stars and planetary disks are forming. It is easily observable from Earth simply with binoculars. This nebula looks like a small cloud in which the central region appears greenish. The Milky Way is a spiral galaxy. It consists of a flat main body in the form of a disk with a diameter of more than 100,000 light-years. This disk contains the vast majority of stars. It contains curved structures from the core that extend to the borders of the galaxy. These are the spiral arms. Inside these arms, the matter reaches a high density, and clouds of gas and interstellar dust give birth to new stars. In the center of the flattened disk, we find the galactic nucleus which shelters the halo, a shell populated by the oldest stars and globular clusters, representing the ancient stellar systems of our galaxy. Globular clusters have an extremely high density and are extraordinary objects that we can contemplate through a telescope from Earth. "27,000 light-years away from the heart of the galaxy, we find the Sun, our star. It is located on the periphery, 2/3 of the galactic radius from the center. We, the inhabitants of the Earth, travel in space, following the movements of our planet, with the whole solar system within the Milky Way. These movements are imperceptible, but they are similar to a crazy race of 600 kilometers per second, or 370 miles per second. The Milky Way rotates on itself in about 240 million years. The Sun orbits around its center at a speed of about 220 kilometers per second, or 136 miles per second. The starry sky that illuminated the Earth at the time of the dinosaurs was therefore very different from the sky we can observe today. During this time, the Sun has gone through at least 1/3 of its revolution. It moves in space with its own motion that is superimposed on the revolution around the galactic center. The stars are subject to the local attraction exerted by the nearby stars. They have their own motion and move through the galaxy. The constellations that we observe did not exist at that time, and they will not exist in the future. One of the particularities of the Milky Way and of any other spiral galaxy is that its rotation occurs in a differentiated way. The central stars and celestial objects have a shorter period of revolution than the more distant stars and objects. The objects that populate the Milky Way, such as open and globular clusters or nebulae, move across the sky. The movement of globular clusters is particularly remarkable. These dense clusters are composed of hundreds of thousands of old stars that inhabit a spherical region around the nucleus and disk of the galaxy. They are like satellites and revolve around the galactic center in elliptical orbits more elongated and inclined than the disk. Their movement is very fast, about 200 kilometers per second, or 125 miles per second, and they regularly cross the disk. Thanks to their density, they remain stable. However, the interaction with the plane of the Milky Way leads to their disintegration. The open clusters have a different motion. Containing only a few hundred or thousands of stars, these clusters break up in the spiral arms. Their stars being less thick than those of globular clusters, they tend to disintegrate over tens of millions of years. Therefore, globular clusters can reach a lifetime of more than 10 billion years, while open clusters are younger. A large band of dust called the Great Rift splits the Milky Way in two. Originally, our galaxy was made up of stars and hydrogen clouds, and we could see through them very well. Since then, countless stellar explosions have released dust that has accumulated inside, completely changing its appearance. When we look towards the interior of the galaxy, the Great Rift is positioned between the constellation of Cygnus and the southern constellation of Centaurus. All spiral galaxies are now crossed by such dust bands. The Milky Way belongs to a group of about 60 galaxies called the Local Group. The Milky Way is not the only galaxy in the universe. Many small, faint nebulae in the night sky are also galaxies. They are distant from the Milky Way. Galaxies are not uniformly distributed in the universe. They form groups more or less large. Large galaxies are usually accompanied by dwarf satellite galaxies. There are two that can be seen with a naked eye from Earth. They appear as nebulae. They are the Magellanic Clouds. 24 other dwarf galaxies of low brightness are next to them. A little further away, we find the great galaxy of Andromeda, itself surrounded by two other, relatively large neighbors, and many small satellite galaxies. The Milky Way, accompanied by the Andromeda Galaxy and the Triangulum Galaxy, forms the local group, with many other smaller galaxies. Counting also the dwarf galaxies, the local group includes more than 50 members. The three large spiral galaxies that are the Milky Way, the Andromeda Galaxy and the Triangulum Galaxy, are accompanied by dozens of smaller galaxies. The satellite galaxies are those present in greater numbers. They swarm around the large spiral galaxies like mosquitoes around a lamp. These satellite galaxies are discrete agglomerations of several million stars of a few thousand light-years in diameter. The Triangulum Galaxy has no satellite galaxies, while the Milky Way and the Andromeda Galaxy are surrounded by many. They probably grew by swallowing small satellite galaxies. This process is still going on today. For example, the Sagittarius dwarf galaxy has been stretched by the tidal forces of the Milky Way and will eventually be swallowed by it. The Large Magellanic Cloud is about 15,000 light-years in diameter. It is composed of a few billion stars and is located 163,000 light-years from Earth. Due to its high content of gas and interstellar dust, the level of star formation activity is very high. The largest star-forming region of the Large Magellanic Cloud is the Tarantula Nebula. It is so bright that if it were located at the same distance as the Orion Nebula, it would never be dark on Earth. The Large Magellanic Cloud contains dozens of globular clusters, hundreds of open stellar clusters and planetary nebulae. It contains many more heavy elements than the Milky Way. These have been created over time by nuclear fusion reactions within the stars themselves, indicating that the Magellanic Clouds are younger than the Milky Way. The brightness of the Magellanic Clouds is incomparable to that of the Milky Way. From the southern hemisphere, and in the absence of light pollution, they appear distinctly to the naked eye. The small Magellanic Cloud is located further away than its big brother, 200,000 light-years from Earth. It contains fewer stars, only 3 billion. It is less bright in the night sky, but it is still recognizable to the naked eye. The small Magellanic Cloud contains a large number of Cepheids. These are stars whose brightness varies over a period of days or weeks. The Andromeda Galaxy is located 2.5 million light-years from Earth. From the northern hemisphere, on a moonless autumn night, and on a clear day, the Andromeda Galaxy appears as a diffuse patch of light. It is one of the most distant objects in the universe that can be seen without the aid of optical instruments. The Andromeda Galaxy contains about 1 trillion stars, at least twice as many as the Milky Way. It is larger than the latter. It is the largest galaxy in the local group. However, it seems to contain fewer star-forming regions. The Andromeda Galaxy was born 5.5 billion years ago from the collision and merger of two smaller galaxies. The Triangle Galaxy owes its name to the constellation in which it is located. This spiral galaxy is located almost 3 million light-years from Earth. It has a low brightness. Nevertheless, under extremely favorable conditions, it is possible to see it with the naked eye from Earth. The Triangulum Galaxy is the smallest of the 3 large galaxies in the local group. It is half the size of the Milky Way, contains about 40 billion stars, and is about 50,000 light-years in diameter. The Triangulum Galaxy is home to a large number of star-forming regions, including the largest, NGC 604. This magnificent nebula in emission surpasses the brightness of Venus. Its gas is ionized by a cluster of massive stars at its heart. Distributed in at least 2 clusters, there are about 200 stars with masses ranging from 15 to 60 solar masses. The diameter of the Triangle Nebula reaches about 1,500 light-years. In about 4 billion years, the local group will see the Milky Way and the Andromeda Galaxy collide. 2 billion years later, they will merge to form a single giant elliptical galaxy. The Sun and its planets could be catapulted into space because of gravitational disturbances. The Triangulum Galaxy, meanwhile, may collide with the Milky Way a little earlier. It may end up orbiting the giant elliptical galaxy that will form during the collision between the Milky Way and the Andromeda Galaxy. Laniakea is a Hawaiian word meaning immense celestial horizon or immeasurable paradise. It is a supercluster of galaxies that includes, among others, the Virgo supercluster, which hosts the Milky Way, and thus our planet Earth. Our local group forms with other galaxies a superstructure in a quasi-central position within the Virgo cluster. The latter is like a vast and flat expanse, including a small central bulge that is called local supercluster. The local cluster represents only one of the 6 million superclusters in the observable universe. Laniakea consists of 3 superclusters: the Virgo supercluster, of which we are a part, the Hydra-Centaur supercluster, in which the Great Attractor is located, and finally, the Peacock-Indian supercluster. As in most galactic clusters, the space between the different galaxies is not really empty. It is filled with rarefied gas, mainly hydrogen and helium, at a temperature of nearly 30 million degrees Celsius, or 54 million degrees Fahrenheit. Laniakea extends over 500 million light-years. This supercluster contains more than 100,000 galaxies. The mass of Laniakea is estimated at about 100 million billion times that of the Sun. Each of the 100,000 large galaxies like ours has an average of 100 billion stars and 1 million dwarf galaxies. The local group is located in the Virgo supercluster. The Hydra-Centaurus supercluster is the closest neighbor of the Virgo supercluster. It is actually 2 superclusters, the Hydra and the Centaur, which are gravitationally connected. The Peacock-Indian supercluster contains 3 main clusters: a Bell 3656, a Bell 3698, and a Bell 3742. At the heart of the Laniakea supercluster is the Great Attractor. This gravitational anomaly in intergalactic space demonstrates the existence of a local concentration of mass equivalent to tens of thousands of times the mass of the Milky Way. Our galaxy, and all those in our supercluster, are heading towards the Great Attractor. If one imagines a picture from the sky that represents the distribution of all the superclusters in the observable universe, the Milky Way is much too small to be visualized. Proportionally, the solar system, the Earth, and man can only be imagined. We are a tiny part of a speck of dust in this vast ocean. This vast ocean in question represents, in our eyes, the so-called observable universe. The further man looks into space, the further he looks into the past. The speed of light is not infinite, but the finite speed of light, combined with the finite age of the universe, delimits an impassable border between which we cannot see. This is the cosmological horizon. Even with the best telescope, everything beyond this limit remains undetectable. Light needs time to reach us, but the possible travel time is limited, since the universe is 13.8 billion years old. Thus, the light from a galaxy, located 20 billion light-years away from us, has not yet had enough time to reach the Earth. It is beyond our cosmological horizon. It is comparable to the horizon that sailors see from the lookout of a ship. The ocean continues just as the universe exists beyond the cosmological horizon. We just can't see it. The expansion of the universe is faster than the speed of light, which is why galaxies are far apart beyond 13.8 billion years. Telescopes do not show the world as it is, but as it was. When we look at the stars, we are in fact looking into the past. The farther we look into space, the farther into the past we see. This phenomenon gives us access to bodies or phenomena that no longer exist, such as stars that exploded in supernovae, galaxies destroyed by tidal forces, or the first years of the universe. Light has a speed of 300,000 kilometers per second. It takes time to reach us. It takes about 8 minutes for the light from the sun to reach us on Earth. When we look at the sun, it appears as it was 8 minutes earlier. When we look at the stars in the night sky, they appear to us as they were tens or even hundreds of years earlier. With the expansion of the universe, the concept of distance loses some of its meaning. When a galaxy is 10 billion light-years away, it means that it has been traveling through an expanding space for all that time before reaching us. When this light was emitted, the galaxy was at a closer distance to us than when its light reaches the Earth. Because of the expansion of the universe, astronomers are able to determine the distance to the most distant galaxies in the observable universe. The light that arrives from a galaxy brings with it a suitcase full of information about the length of its journey. The most distant star ever observed is nicknamed Icarus. This blue supergiant is located 9 billion light-years away from us. The galaxy Z8 5296 is one of the most distant galaxies and one of the oldest currently known. It would have formed some 700 million years after the Big Bang. Although it is 13.1 billion years old, it is actually about 30 billion light-years away from Earth due to the expansion of the universe. This galaxy appears rich in metals and would generate 100 times more new stars than our Milky Way. Although Laniakea is a most impressive superstructure, it represents only 4% of the observable universe. So what would happen if we took into account the universe as a whole? A long time ago, men thought that our planet Earth was unique. Then we discovered that there were other planets orbiting a star, the Sun. A long time ago, people thought that the Sun was unique. Then we discovered the Milky Way and its hundreds of billions of suns. A long time ago, men thought that the Milky Way was unique. Today we know that the observable universe contains 100 billion galaxies. Is it possible that humans will one day discover that there are other universes beyond the one we are able to observe? To know our place beyond the universe, we would already have to know what it contains. However, this area is currently inaccessible to us. Only hypotheses are put forward by scientists to explain what can be found beyond. The universe that we can observe from the Earth is full of galaxies that extend in all directions. We see them more than 10 billion light-years away. But the galaxies must extend much further. On this subject, speculations abound and address without complex the existence of parallel universes. The string theory of particle physics approaches the notion of multiverse. The different universes of this multiverse would each have unique properties. They could exist in parallel to each other, but in different dimensions. Science also allows us to imagine that beyond the observable universe, space is infinite, and without limit since its creation, it has not stopped growing. The cosmos could then extend perpetually. Hundreds of billions of light-years away from us, there may be another universe similar to ours. In this other parallel universe, would life exist? All research conducted to date in the areas we can reach remains unsuccessful. Beyond the Sun, the Milky Way contains between 200 and 400 billion stars. It is itself only one galaxy among 100 billion other galaxies. Many stars are surrounded by a procession of planets. The list of planetary systems discovered is growing every year. A universe modestly filled with billions of planets could well hide other places where the miracle of life could have taken place. For more than half a century, thanks to highly sensitive detectors and high-tech computers, we have been sending mathematically coded messages to neighboring exoplanetary systems to let them know we are there. But the cosmos remains desperately silent. While it is possible that life is widespread in the universe, complex life forms and intelligent civilizations would certainly be rarer. Perhaps we are a subject of observation for a scientific experiment conducted by an advanced alien life form. Or are we unable to understand them because their technology is much more advanced than ours? Or are we simply the only living beings in the universe? The universe is extremely vast, with billions of galaxies each containing hundreds of billions of stars. Seen from this eye, man occupies a relatively insignificant place. Our planet Earth, being only a small rocky planet orbiting a medium-sized star, the Sun, located in a relatively quiet galactic suburb. Although we have explored and observed much of the observable universe through technology, our understanding remains limited. We know that the universe is expanding and that visible matter, such as stars, galaxies, and planets, is only a small fraction of the total matter in the universe. Man has not yet succeeded in fully understanding the immensity and complexity of the universe that surrounds him. Despite our modest place in the universe, we have developed the ability to think, reason and understand the physical laws that govern our environment. We have created a technology that allows us to explore and study the universe in which we live. We're on our way to the local group. We've got a long way to go, since just to get out of the Milky Way we'd need thousands of light years. In the meantime, let's take a look at the history of the local group. Where does the term local group come from? The first to use it was the German astronomer Walter Body in 1935 in a publication about the globular cluster NGC 2419 or Caldwell 25. For the record, this globular cluster is located in the Lynx constellation, some 300,000 light-years from us. It's nicknamed the Intergalactic Vagabond, as it seems to have belonged to the Milky Way before, but eventually broke away from it. NGC 2419 is also part of the local group. The term local group was coined in 1936 by the American astronomer Edwin Hubble, after whom NASA's famous telescope is named. Edwin Hubble developed Hubble's law, according to which galaxies move away from each other at a speed roughly proportional to their distance. In other words, the further away a galaxy is from us, the faster it seems to be moving away. This law was the first proof of the expansion of the universe, stating that it is not the galaxies, planets, and stars that are moving, but the space between them that is increasing. In the 1930s, when the local group concept first emerged, not so many galaxies had been discovered. Edwin Hubble first counted just a few galaxies in the local group. The Milky Way and the Andromeda Galaxy, of course, but also the Large Magellanic Cloud, the Small Magellanic Cloud, M32 NGC 205, the Triangulum Galaxy, Barnard's Galaxy, and IC 1613. The local group concept was later used in a publication by American astronomer Walter Body in 1944, in which he established that the galaxies NGC 147 and NGC 185 belonged to the local group. It was Body who brought the number of galaxies in the local group up to 18 by adding a few more to the list: the Dragon, Furnace, Leo 1, Leo 2, Sculptor, Little Dipper, and IC 5152 galaxies. The IC 5152 galaxy was subsequently excluded from the local group galaxy list, however, as it is too distant, at 5.8 million light-years from us, to belong to our group of galaxies. During the second half of the 20th century, other galaxies were discovered and added to this list, notably dwarf galaxies. A dwarf galaxy is a small galaxy made up of 100 million to a few billion stars. By comparison, the Milky Way contains 200 to 400 billion stars. Dwarf galaxies often orbit larger galaxies, as is the case in the local group, where we find dwarf galaxies concentrated around the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy, the three largest galaxies in the local group. Over 30 dwarf galaxies have been identified, orbiting our Milky Way galaxy, including the Large Magellanic Cloud, the largest, and the Carina Dwarf Galaxy, the smallest. In 2000, there were officially 38 galaxies in the local group. Today, there are over 50. It's hard to say with any certainty how many galaxies are in the local group. Not only can't we detect all the galaxies, because some are much less luminous than others, but we still don't really know where the local group ends. What we do know today about the local group is that it is built around two spiral galaxies, the Andromeda Galaxy, or M31, and the Milky Way. Each of these two spiral galaxies is surrounded by satellite galaxies. Surrounding the Milky Way are the two Magellanic Clouds and many other galaxies whose names may be familiar to you: the Big Dog, Sagittarius, Little Dipper, Dragon, Carina, Sextant, Sculptor, Furnace, Leo 1, Leo 2, and Toucan galaxies. Surrounding the Andromeda Galaxy are the galaxies M32, the Triangulum Galaxy M33, M110, NGC 147, NGC 185, and Andromeda 1, 2, 3, and 4. The Triangulum Galaxy also has a satellite galaxy, the Pisces Dwarf Galaxy. On this journey to the heart of the local group, we'll be taking a closer look at each of the main satellite galaxies of the Milky Way and Andromeda galaxies. But when we talk about satellite galaxies, we don't mean that they're completely glued to the galaxies around which they orbit. To give you an idea, the Great Dog Galaxy, the closest satellite galaxy to the Milky Way, is located 25,000 light-years from our galaxy. Apart from the two main galaxies and their satellite galaxies, the local group also includes galaxies independent of these subgroups, which we'll be observing at the end of our journey to the far reaches of the local group. We've now reached our destination. It's time to take a closer look at the local group. The local group is located at the edge of a giant supercluster of galaxies, the Virgo supercluster. Also known as the local supercluster, the Virgo supercluster is a supercluster of galaxies comprising the local group, and at its center, the Virgo cluster. It comprises around 10,000 galaxies, and much of its mass is probably dark matter. As the universe expands, the local group is moving away from the Virgo cluster, and therefore from the center of the Virgo supercluster. The local group extends over a diameter of around 10 million light-years. It contains every type of galaxy except giant elliptical galaxies, which are not found in such small structures. That's right, because the local group, despite its 10 million light-year diameter, is not considered a large structure by comparison with other galaxy superclusters. We can't know the exact number of galaxies in the local group. Some are too faint, others are obscured by the Milky Way. Depending on the source, you may hear talk of 60 or 80 galaxies. In any case, there are more than 50. In the local group, there are three spiral galaxies: the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy. Spiral galaxies account for 3/4 of the galaxies listed in Hubble's classification of galaxy types, developed by Edwin Hubble in 1936. Their structure is particularly complex compared to that of elliptical galaxies. Spiral galaxies consist of a flattened disk containing a few 100 billion stars and a luminous spherical central bulge known as the bulge. Two or more luminous arms extend from the disk, spiraling around the bulge. The center of the disk rotates faster than the edges. Barred spiral galaxies like the Milky Way are distinguished from ordinary spiral galaxies. Barred spiral galaxies have a linear structure instead of two spiral arms. Spiral galaxies also contain a lot of gas and dust. The arms of a spiral galaxy are made up of these gases, as well as the youngest and brightest stars. Scientists believe that spiral galaxies have this spiral shape at the beginning of their lives when they contain a lot of gas, and then gradually lose their rotation and become elliptical as galaxies merge. The local group also contains two Magellanic spiral galaxies, the Large Magellanic Cloud and NGC 3109. This type of spiral galaxy has only one spiral arm, and is smaller than an ordinary or barred spiral galaxy. Only one elliptical galaxy has been identified in the local group, M32, which is a satellite of the Andromeda Galaxy. Elliptical galaxies differ from spiral galaxies primarily by their elliptical shape, but not only. Unlike spiral galaxies, they don't contain a gas disk where young stars can form, and the movement of stars is random, whereas in spiral galaxies, stars are in rotation. Elliptical galaxies are made up of old stars, which is why scientists believe they form when two spiral galaxies collide. In the local group, M110 and NGC 147 are dwarf elliptical galaxies, a type often found in galaxy clusters and often companions to other larger galaxies. The majority of local group galaxies are spheroidal dwarf galaxies, galaxies that are more or less spherical in shape and small in size, i.e., with a few million to a few hundred million stars. Spheroidal dwarf galaxies are ancient and have evolved very little, and their composition resembles that of globular clusters, very dense concentrations of spherical stars orbiting galaxy nuclei. Finally, the rest of the local group are irregular galaxies. These galaxies show no regular structure, being neither spherical, elliptical, nor spiral-shaped. Most irregular galaxies are dwarf galaxies, rich in bright stars and therefore very luminous. Even so, they are difficult to detect because of their small size. Scientists believe that this type of galaxy was once very common in the universe, but that collisions reduced their number. Today it is estimated that at least 10% of all galaxies are irregular. We're now going to take a closer look at each of the main galaxies identified as part of the local group, from the galaxy closest to us to the most distant. The Milky Way, our galaxy, is the second largest galaxy in the local group. It's also known as the galaxy with a capital G. It's a spiral galaxy, home to between 200 and 400 billion stars, including the Sun, and probably over 100 billion planets. The Milky Way's diameter is estimated at 100,000 to 120,000 light-years, perhaps even as much as 200,000 light-years. The center of the galaxy is a supermassive black hole, Sagittarius A, and the solar system is located 27,000 light-years from this center, so it's more on the periphery. Stars revolve around the center of the galaxy, and the Sun takes around 250 light-years to complete a full circle. Since it came into being, the Sun has made only about 20 revolutions. You may be wondering why our galaxy is called the Milky Way. When seen from the sky, the Milky Way looks like a white streak, like a milky flow of stars. In Greek mythology, the origin of the Milky Way is explained in an imaginative way. The Greeks recounted that Zeus had had an illegitimate child, Heracles, with his mistress, Alcmene. Zeus, wishing to make his son immortal, took advantage of a moment when his wife Hera was dozing to lay the infant Heracles on her breast. He begins to suckle Hera, but she wakes up and realizes that this is not her real child. So she forcefully pushes him away, leaving a trail of milk in the sky that will become the Milky Way. The Milky Way has also often been likened to a river. The Egyptians thought it was a copy of the Nile in the sky. The Chinese called it the Silver River, and the Japanese the River of Paradise. This idea of a river in the sky can be found in several Asian mythologies. Lastly, it could also have religious connotations, as was the case with the Mayans, who believed it to be a religious path, enabling souls to reach paradise. In 1610, Galileo was the first to show that the color of the band formed by the Milky Way in the sky was due to the presence of numerous stars. It wasn't until the 1920s, however, that Edwin Hubble proved that the Milky Way was just another galaxy. In the 1930s, the Milky Way's galaxy model was established, a barred spiral galaxy. The Milky Way has 6 spiral arms, which in turn divide into other spiral arms. The arm of Perseus, the arm of the ruler, the arm of the swan, the arm of the cross, the arm of Sagittarius, and the arm of Orion. Our solar system is located in the Orion arm. If the Milky Way appears to us as a flat disk in the sky, it's because we see it from the edge. According to researchers, our galaxy was formed by the merging of several dwarf galaxies that appeared 800,000 million years after the Big Bang, during a phase of very active star formation. There are many different types and ages of stars in our galaxy. In fact, the oldest star in the Milky Way, HE 1523-0901, is 13.2 billion years old, so it appeared shortly after the Big Bang. This is the scenario that has so far been accepted to explain the formation of the Milky Way. 13 billion years ago, 2 galaxies began to form stars independently of each other. On one side was a dwarf galaxy, Gaia Enceladus, and on the other, a galaxy 4 times more massive and richer in metals. 10 billion years ago, these 2 galaxies collided. Some of their stars were ejected into chaotic orbits, forming the Milky Way halo. For 4 billion years, violent episodes of star formation followed one another, until around 6 billion years ago. The remaining gas settled into the Milky Way's disk, which we can still observe today. Surrounding the Milky Way are orbiting dwarf galaxies, including the Small Magellanic Cloud and the Large Magellanic Cloud, which are visible to the naked eye from Earth in the southern hemisphere. The Great Dog Dwarf Galaxy is the closest known satellite galaxy to us. It is located in the Big Dog constellation, 42,000 light-years from the center of the Milky Way and 25,000 light-years from our solar system. It is an irregular dwarf galaxy and contains 1 billion stars, equivalent to 1% of the Milky Way. It was discovered rather late, in 2003, because it lies behind the plane of the Milky Way, where clouds of gas and dust are denser. However, this galaxy may no longer exist in the future. The tidal forces of the Milky Way are tearing it apart. At present, the center of the Great Dwarf Dog Galaxy is badly degraded, with a long filament of stars trailing behind it, 3 times around the Milky Way. This filament of stars is sometimes referred to as the unicorn ring, and it was this filament that enabled scientists to discover the Great Dwarf Dog Galaxy. Let's continue a little further. 80,000 light-years from Earth and 50,000 light-years from the center of the Milky Way lies the dwarf Sagittarius galaxy. This galaxy is thought to be elliptical or spheroidal, and should not be confused with the irregular Sagittarius dwarf galaxy. In fact, we don't know whether it's spherical or elliptical, as it's being stretched by the tidal forces of the Milky Way. The Sagittarius dwarf galaxy was discovered in 1994. At the time, it was the closest known galaxy to our own. It too is rather difficult to observe, as it is diametrically opposed to the solar system in relation to the center of our galaxy. Spectroscopic analyses have shown that this galaxy is probably very old. It is made up only of old metal-poor stars, known as population 2. Scientists predict that it will eventually be absorbed by the Milky Way. A little further on, the Large Magellanic Cloud is a barred Magellanic spiral galaxy. With a diameter of 14,000 light-years, it is the fourth most massive galaxy in the group, after the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy. The Magellanic Spiral Galaxy is a type of spiral galaxy with a single spiral arm. This type was coined for the Large Magellanic Cloud by French astronomer Gérard de Vaucouleurs when he revised Hubble's classification. Unlike the other two satellite galaxies we've seen so far, the Large Magellanic Cloud can be seen from Earth, more precisely from the southern hemisphere. In fact, it was discovered much earlier than the Great Dog and Sagittarius dwarf galaxies, since it was first mentioned in 964 by a Persian astronomer by the name of Abd al-Rahman al-Sofi. The Large Magellanic Cloud could collide with the Milky Way long before the Andromeda Galaxy. It is home to some remarkable celestial objects, including the Tarantula Nebula, a region of ionized hydrogen, or HII, and the largest nebula known to date. In this zone, the star-birth rate is higher than in any other region of our galaxy. The Large Magellanic Cloud also contains stellar black holes, celestial objects created by the evolution of the most massive stars after their supernova explosion. There's also a soft gamma-ray star, SGR 0526-66, a source of gamma rays that is probably linked to young neutron stars with strong magnetic fields. The Large Magellanic Cloud is linked to the Small Magellanic Cloud by a bridge of gas and stars called the Magellanic Bridge. The Small Magellanic Cloud is an irregular galaxy located in the Toucan constellation and is one of the most distant celestial objects visible to the naked eye. However, like the Large Magellanic Cloud, with which it forms a pair, you can only see it from the southern hemisphere, far from light pollution. Like the Large Magellanic Cloud, the Small Cloud was first mentioned by navigator Amerigo Vespucci in a voyage report from 1503 to 1504, but it was Magellan's expedition that gave it its name. The Small Magellanic Cloud is thought to have been a barred spiral galaxy, distorted by the tidal forces of the Milky Way. The Bouvier dwarf galaxy lies close to both Magellanic Clouds. We are now 195,000 light-years from the Sun. This spheroidal dwarf galaxy is located in the constellation du Bouvier, hence its name, and was discovered in 2006. Its luminosity is estimated at 100,000 times that of the Sun, which is very low for a galaxy. The Bouvier dwarf galaxy is strongly disrupted by the tidal forces of the Milky Way. It is composed mainly of very old stars, aged between 13.3 and 13.4 billion years. Let's continue our journey to discover the Milky Way's satellite galaxies. Just 205,000 light-years from our solar system lies the Little Dipper Dwarf Galaxy, a spheroidal galaxy, located, as you may have guessed, in the Little Dipper constellation. This galaxy was discovered in 1955 thanks to a photographic survey of the night sky carried out at the Palomar Observatory, 80 kilometers north of San Diego, California. Like almost all of the Milky Way's dwarf satellite galaxies, the Little Dipper Dwarf Galaxy is essentially composed of old stars with little interstellar matter. A little further away, 260,000 light-years from us in the constellation of the Dragon, the Dwarf Dragon Galaxy was also discovered, thanks to photographic surveys by the Palomar Observatory. This spheroidal dwarf galaxy is one of the least visible satellite galaxies because it is so faint. "280,000 light-years away, the Sextant Dwarf Galaxy is a spheroidal dwarf galaxy discovered in 1990. It too is not very luminous and is one of the least luminous nearby galaxies. Just next door, 285,000 light-years away, the Sculptor Dwarf Galaxy was the first spheroidal dwarf galaxy in 1937. Analysis of its composition has revealed that it is similar to the primitive galaxies observed at the edge of the universe. Let's continue a little further afield. There are still more satellites of the Milky Way to observe. The Carina Dwarf Galaxy, 330,000 light-years away, is a spheroidal dwarf galaxy that formed a little more recently than the others. Most of its stars are thought to have formed 7 billion years ago, although analyses have also revealed periods of star formation as far back as 13 billion years ago, and as recently as 3 billion years ago. This galaxy was discovered in 1977 and is around 75 times smaller than our own galaxy, with a diameter of 1,600 light-years. It is moving away from the Milky Way at a speed of 230 kilometers or 140 miles per second. Recently discovered in 2018, the dwarf galaxy Antlia 2 is located 422,000 light-years from us. As you can see, its size is relatively close to that of the Large Magellanic Cloud, but its luminosity is 10,000 times fainter. In fact, it's the least luminous galaxy ever discovered. That's certainly why it was only discovered late in 2018, when most of the galaxies in the local group were already known at the end of the 20th century. The Furnace Dwarf Galaxy is located around 450,000 light-years from us. It is also a spheroidal dwarf galaxy, composed of ancient stars, and shines faintly. Several globular clusters have been detected, including NGC 1049, which is brighter than the galaxy itself. NGC 1049 was discovered a century before the Furnace Dwarf Galaxy. Let's move on a little further to observe the Lion 2 Galaxy 700,000 light-years away and the Lion 1 Galaxy 800,000 light-years away. Both are spheroidal dwarf galaxies. The Leo 1 galaxy is remarkable for containing very little dark matter, compared with the Milky Way's other satellite galaxies. In 2021, a supermassive black hole of 3.3 million solar masses was discovered at its center. We've now arrived at the Milky Way's last satellite galaxy, the Phoenix Dwarf galaxy. Scientists don't know whether this is a spheroidal dwarf galaxy or an irregular one. Perhaps that's why, when it was discovered in 1976, it was classified as a globular cluster, only to realize a year later that it was in fact a galaxy. This short tour of the Milky Way's satellite galaxies would not be complete without mentioning the Lion A galaxy, located 2.25 million light-years from us. The problem is that we don't really know whether the Lion A galaxy is a satellite of the Milky Way or belongs to the group of galaxies known as Antlia sextans. We'll be looking at this group of galaxies a little later in the trip, as it's located even further out on the periphery of the local group. Let's continue our journey towards the other galaxies of the local group. We're now 1.63 million light-years from the Milky Way, in front of Barnard's galaxy, or NGC 6822. This galaxy is a barred irregular galaxy. Simply put, it's the irregular version of a barred spiral galaxy like the Milky Way. Barnard's galaxy was so named because it was discovered in 1881 by the American astronomer Edward Emerson Barnard, who also gave his name to Barnard's star. The Barnard galaxy contains only around 10 million stars, most of them young. Edwin Hubble identified 15 variable stars in this galaxy. Variable stars are stars whose luminosity varies over shorter or longer periods of time. The Sun, on the other hand, is almost constant in brightness, varying by 0.1% over an 11-year cycle. Today, over 150 HII regions have been identified in this galaxy. Previously, it was thought that the universe stopped at 300,000 light-years. The discovery of Barnard's galaxy brought home the true size of the universe. We are now approaching the Andromeda Galaxy, the largest galaxy in the local group, with a diameter of 220,000 light-years. This spiral galaxy is also known as NGC 224, or M31, in the Messier catalog of nebulae and star clusters. This catalog, drawn up in 1774 by French astronomer Charles Messier, was intended to help comet hunters avoid confusing comets with diffuse objects such as nebulae or star clusters. The Andromeda Galaxy is located 2.55 million light-years from the Sun in the Andromeda constellation. Until the 1920s, it was thought to be a nebula rather than a galaxy. It is thought to contain around 1,000 billion stars, 2 to 5 times more than our own galaxy. Its total luminosity would be 26 billion times that of the Sun, or 25% more than our galaxy. But the Milky Way's star formation rate is 3 to 5 times higher than that of the Andromeda Galaxy, and there are twice as many supernovas in our galaxy. Perhaps one day, the Milky Way's luminosity will exceed that of the Andromeda Galaxy. Because it's so luminous, the Andromeda Galaxy is one of the few galaxies you'll be able to observe with the naked eye in the northern hemisphere. If you look carefully, you can't miss it. Its apparent diameter is 6 times the apparent diameter of the Moon from the Earth. In fact, it was discovered a long time ago. The first known written mention of this galaxy dates back to 964 by Abd al-Rahman al-Sofi in his Book of Fixed Stars. However, it wasn't until 1612 that it was observed through a telescope by the German astronomer Simon Marius, the same man who named Jupiter's 4 main satellites, the Galilean moons. The Andromeda Galaxy was first photographed in 1887 by British astronomer and pioneer of nebula photography, Isaac Roberts. The Andromeda Galaxy is thought to have formed recently. For astronomers, this means less than 3 billion years ago. At the time it formed, the Earth certainly already existed. The Andromeda Galaxy is thought to be the result of the collision of 2 galaxies. Like the Milky Way, it contains a supermassive black hole at its center, called M31. In around 4.5 billion years' time, an observer on Earth will be able to see the Andromeda Galaxy in the night sky as a pinkish cloud of dust. This is because the Andromeda Galaxy and the Milky Way are about to collide. This collision will have many effects. Firstly, it will cause the collapse of the galaxy's gas clouds. Secondly, it will give rise to new stars. Some stars will be sucked into the black hole, while others will be ejected into intergalactic space. The galaxies, for their part, will merge to form a large elliptical galaxy. Their 2 supermassive black holes will also merge to form an even larger black hole. Around the Andromeda Galaxy, there are also satellite galaxies like those around the Milky Way. The most important of these is the Triangulum Galaxy, or M33, which is the 3rd most massive galaxy in the local group, with a mass 60 billion times that of the Sun. It is also a spiral galaxy. Perhaps you've already heard of this galaxy, home to the fictional planet Vinea in the science fiction comic strip Yokosuno, and the planet Gliese in Jean-Gaston Vandel's futuristic trilogy. In reality, we don't really know whether the Triangulum Galaxy is a satellite of the Andromeda Galaxy, but we assume it is. The 2 galaxies are separated by a distance of 750,000 light-years. We are now some 3 million light-years from our solar system. Although the Triangulum Galaxy was first catalogued by Charles Messier in his catalogue as M33, it had probably been observed before. Under the right conditions, you can even observe it with the naked eye from Earth, more precisely from the southern hemisphere. In fact, mentions of this object have been found as far back as 1850. The Triangulum Galaxy is a regular, unbarred spiral galaxy, but it does have a bar running 2,600 light-years through its center. At the heart of this galaxy is not a supermassive black hole, but an HII region containing an ultra-luminous X-ray source. ULXs are still enigmatic objects for science. What we do know is that they are ultra-powerful X-ray sources. In fact, the ultra-luminous X-ray source in the Triangulum Galaxy is the most powerful X-ray source in the local group. The Triangulum Galaxy is home to other remarkable celestial objects, starting with several HII regions, the brightest of which, NGC 604, may have undergone a burst of star formation as recently as 3 million years ago. 54 globular clusters have been identified around the Triangulum Galaxy, but there are certainly more than double that number. At equal distance from the Triangulum Galaxy and the Andromeda Galaxy, 2.5 million light-years from us, you can see the Pisces Dwarf Galaxy or LGS-3. This galaxy could be a satellite of the Andromeda Galaxy or the Triangulum Galaxy, if the latter is not a companion of the Andromeda Galaxy. This irregular dwarf galaxy was discovered in October 1978 in a search for satellite galaxies of M31 and M33. 5 objects were cataloged and grouped together under the name Local Group Suspect, hence the name LGS-3. The Pisces dwarf galaxy was the only one of the 5 objects to be confirmed as a local group galaxy. The Pisces dwarf galaxy contains old, metal-poor stars, but also atomic hydrogen gas, which may indicate the presence of young stars. It may therefore be a transitional object between a spheroidal dwarf galaxy and an irregular dwarf galaxy. What interests scientists about this small galaxy is the presence of a high-speed cloud called HVC 127-41-330. In this high-speed cloud, which is probably gravitationally interacting with the Pisces dwarf galaxy, no stars have been detected. And yet, it has a diameter of 20,000 light-years. What's more, HVC 127-41-330 could be 80% dark matter. So, according to American astronomer Josh Simon, it could be the first dark galaxy observed in the universe. A dark galaxy is a hypothetical type of galaxy that is devoid of stars, or at least produces very few of them. If their existence is confirmed, these galaxies would be extremely difficult to detect, as they would be totally obscure. Theoretical models of galaxy formation suggest that dark galaxies are the first stage in the long process of galaxy formation. Observing one would be a giant step towards understanding the formation of our own galaxy. Although the Andromeda Galaxy's satellite galaxies, a dozen or so, are, like the Pisces dwarf galaxy, closer to us than the Andromeda Galaxy itself. Let's start with NGC 185, a spheroidal dwarf galaxy that you'll also see under the name Caldwell 18. Discovered in 1787 and recognized as a member of the local group in 1944, this galaxy is located 2.1 million light-years from us in the constellation Cassiopeia. It appears to be gravitationally linked to NGC 147, or Caldwell 17, another spheroidal dwarf galaxy and companion of the Andromeda Galaxy. The two form a stable binary system. At the same distance from the Andromeda Galaxy as the Triangulum Galaxy is the irregular dwarf galaxy IC10. Located 2.15 million light-years from us, it belongs to the Cassiopeia constellation. Discovered as a celestial object in 1889, it was not identified as a galaxy until 1935. It was Edwin Hubble once again who hypothesized that it belonged to the local group. This was confirmed in 1966 by the measurement of its radial velocity. Smaller than the Small Magellanic Cloud, it is nevertheless as luminous as that galaxy. Its active star-forming phase lasts longer than that of the Small Magellanic Cloud, so there are several generations of stars in this galaxy. On the other hand, it is rapidly consuming its reserves of interstellar gas, which will certainly be exhausted in just a few billion years. This galaxy continues to amaze scientists, as it is also home to one of the most massive stellar black holes known, with a mass several dozen times that of the Sun. Around 2.3 million light-years away, we also find the Andromeda 2 galaxy, a spheroidal dwarf galaxy discovered in 1972, along with other galaxies named Andromeda 1, Andromeda 3, and Andromeda 4. Like the Pisces dwarf galaxy, Andromeda 2 is located between M31 and M33, so it's not clear which galaxy it's a satellite of, but scientists are leaning towards the Andromeda galaxy. Andromeda 3, 2.5 million light-years away, is also a spheroidal dwarf galaxy. No stars are thought to be forming in this galaxy, as it contains only old stars, either the same age as those in the Milky Way, or some 3 billion years younger. On the other hand, 56 variable stars have been identified. Irregular dwarf galaxy IC 1613, located roughly between Andromeda 2 and Andromeda 3 in the Cetus constellation, has the shape of a spiral galaxy, but the characteristics of both irregular and spheroidal galaxies. It contains very little cosmic dust, making it easy for astronomers to probe its contents. On the other hand, it is very dim, so you won't be able to observe it with the naked eye. We're still 2.5 million light-years away. You can also see the Andromeda 7 galaxy, also known as the Cassiopeia spheroidal dwarf galaxy, which was discovered in 1998. This galaxy is interesting because it is the brightest and most massive of all the spheroidal dwarf galaxies that are satellites of the Andromeda galaxy. It also has the highest metallicity. Its stars are rather old, with 90% of them having formed 5 billion years ago. Not far away is M32 or NGC 221, an elliptical galaxy that is also made up mainly of old stars and has therefore not experienced a period of star formation for a long time. Scientists believe that M32 was originally a spiral galaxy that crossed the galactic disk of the Andromeda galaxy. It would then have lost most of its peripheral mass. It shows signs of a supermassive black hole at its center. Also nearby is the Whale dwarf galaxy, a low-brightness galaxy, like most spheroidal dwarf galaxies. However, it is not a satellite of the Andromeda galaxy. Indeed, this galaxy is too far away to be a satellite, so it's referred to as an isolated spheroidal dwarf galaxy. These galaxies are quite rare in the local group, but the Whale dwarf galaxy is not the only one. The Toucan dwarf galaxy, for example, is also an isolated spheroidal dwarf galaxy. Analyses carried out with a Hubble telescope have enabled scientists to establish that for 8 billion years, there has been no star formation in this galaxy. Four other satellite galaxies of the Andromeda galaxy are located further away from us than M31. These are Andromeda 1, Andromeda 5, M110, and Andromeda 6. Andromeda 1 was discovered at the same time as Andromeda 2, 3, and 4. This spheroidal dwarf galaxy is located 2.6 million light-years from us, and 150,000 light-years from the Andromeda galaxy. It is the least luminous galaxy, in which a globular cluster has been found. Andromeda 5 was discovered 25 years after the first four Andromeda galaxies. It is an unremarkable dwarf spheroidal galaxy, except for its high metallicity. M110, or NGC 205, 2.7 million light-years away, is more interesting to scientists. This elliptical galaxy contains unusual levels of molecular and ionized gas and dust. What's more, its stars follow random motions, while the galaxy itself is animated by a rotational motion. Several globular clusters have been detected in this galaxy, all of which contain old stars, except the one near the galaxy's heart. The last satellite of the Andromeda Galaxy, Andromeda 6, also known as the Pegasus spheroidal dwarf galaxy, is thought to be located 3.1 million light-years from M31, and not 2.7 million light-years away, as has long been thought. It should not be confused with the irregular Pegasus dwarf galaxy, DDO 216, which is also a satellite of M31 in the Pegasus constellation. Let's go back a little further to 2.8 million light-years away, where we find the Toucan dwarf galaxy we mentioned earlier. This spheroidal dwarf galaxy is unusual in that it is neither a satellite of the Milky Way nor of the Andromeda Galaxy, like the Whale dwarf galaxy. What intrigues scientists is that it lies almost opposite the other members of the local group in relation to the Milky Way. Unlike other isolated spheroidal dwarf galaxies, the Toucan galaxy is not currently undergoing a period of star formation. In fact, this galaxy appears to be gas-free. It is thought to have been star-forming for around 1 billion years, 13 billion years ago. For the last 8 billion years, no new stars have formed. In fact, the Toucan galaxy is thought to have approached the Andromeda Galaxy around 11 billion years ago, ejecting it far out to its present position. Such galaxies are known as counter-current galaxies. "3 million light-years away, the Wolf-Lundmark Melot WLM galaxy is an irregular barred dwarf galaxy that is not a satellite of either the Milky Way or the Andromeda Galaxy. It is located in the Whale constellation. It had already been observed in 1909 by German astronomer Max Wolf, but was not classified as a galaxy until 1926 by Swedish astronomer Knut Lundmark and British astronomer Philbert Jacques Melot, hence its name. Half of the stars in the WLM galaxy are over 9 billion years old. However, between 1 and 2.5 billion years ago, star formation resumed, particularly in the bar, so there are also young stars in this galaxy. Stars are currently forming in this galaxy. Because it lies at the edge of the local group, the Wolf-Lundmark Melot galaxy has been relatively protected from mergers and interactions with other galaxies, making it an interesting one to study. The dwarf Aquarius galaxy, also known as DDO 210, is another isolated irregular galaxy, located 3.3 million light-years from us. It is in fact part of a group of irregular galaxies that do not appear to belong to any particular subgroup. This galaxy is of interest to scientists because it shows a blue shift. The blue shift is different from the red shift, which you've probably heard of. In a nutshell, the red shift is the spectral evidence emitted by celestial objects that are moving away, such as galaxies, but also planets. Redshift is one of the evidences of the expansion of the universe. Well, the blue shift is the opposite phenomenon. The blue shift is spectral evidence that objects are moving closer to us. The Andromeda Galaxy, which is approaching us and will collide with the Milky Way in a little over 4 billion years' time, shows a blue shift. The same applies to the Dwarf Aquarius galaxy. It is approaching our solar system at a speed of 137 kilometers per second, or 185 miles per second. The Dwarf Aquarius galaxy is one of the few local group galaxies for which we can rule out a past proximity to the Milky Way, or M31. In other words, based on its current position and velocity, scientists have deduced that it has not in the past been located close to one of the two most massive galaxies in the local group. Like the Wolf-Lundmark-Melotte galaxy, the Dwarf Aquarius galaxy still contains significant quantities of hydrogen, enabling it to support star formation, albeit at a relatively low level. The median age of stars in this galaxy is 6.8 billion years. This makes it the galaxy in the local group with the youngest median age of stars, after the Leo A galaxy. For this reason, scientists have speculated that the late star formation may be linked to the galaxy's isolation. Do you remember that we observed the Sagittarius dwarf galaxy earlier on this trip? This satellite galaxy of the Milky Way is the second closest to us, after the Big Dog galaxy. We're now looking at the irregular dwarf Sagittarius galaxy, not to be confused. The first, 80,000 light-years away, is elliptical or spheroidal. The second is irregular and lies 4.2 million light-years from us, i.e., very close to the borders of the local group. In short, one is very close to us, the other very far away. The irregular Sagittarius dwarf galaxy was discovered in 1977. As it is very close to the local group boundary, we don't really know for sure whether it belongs to this group of galaxies. In any case, if it does belong to the local group as we assume, it's the farthest local group member galaxy from its center of gravity. Far more luminous than the Dwarf Aquarius galaxy we've just observed, it would have experienced a longer period of star formation and possesses a large number of intermediate-age stars. Most of the stars in this galaxy would therefore be between 4 and 8 billion years old. Just 4.2 million light-years away, another galaxy is located on the outskirts of the local group in the Big Dipper constellation, UGC 4879. This is one of the most isolated galaxies in the local group. It is an irregular dwarf galaxy. It is separated from its nearest neighbor, the Leo A galaxy, by 2.3 million light-years, the distance between the Milky Way and the Andromeda galaxy. It would seem, however, that this galaxy is getting closer to us. UGC 4879 behaves strangely, intriguing astronomers. The vast majority of its stars formed during the first 4 billion years after the Big Bang. Nothing happened for the next 9 billion years until fairly recently, when star formation resumed. In any case, analyses of this isolated galaxy have shown that it probably contains dark matter and a stellar disk. This solitary galaxy has not interacted with other galaxies, making it particularly interesting material for astronomers seeking to understand the complexity of star birth in the universe. When we were looking at the Lion A galaxy earlier in this journey, we mentioned the Antlia Sextans group. Now that our journey is drawing to a close, it's time to take a closer look. The Antlia Sextans group is a small group of galaxies located in the Hydra, Sextans, Leo, and Pneumatic Machine constellations. On average, it lies 4.3 million light-years from us, at the very edge of the local group. For this reason, this group of galaxies is sometimes considered to be outside the local group. Many researchers say that the Antlia Sextans group is an independent group. This group of galaxies includes NGC 3109, the Sextant A and B galaxies, the Leo P galaxy, and the Pneumatic Machine dwarf galaxy. Let's start with NGC 3109. This small, barred Magellanic spiral galaxy, 24,000 light-years across, is located in the Hydra constellation, some 4.35 million light-years from us. It's a so-called low-surface brightness galaxy, meaning that seen from Earth, its brightness is less than 1 magnitude lower than that of the night sky. So far, so good. Most dwarf galaxies are low-surface brightness galaxies. NGC 3109 does, however, have some original features. It has a very low metallicity, like the Small Magellanic Cloud, and contains an unusually high number of planetary nebulae for its low luminosity. A planetary nebula, which is in fact nothing like a planet, is a large cloud of gas created by a giant star at the end of its life, which becomes unstable and starts ejecting its upper layers. Planetary nebulae are magnificent celestial objects with beautiful colors. Analysis of the radial velocity of the disk deformation of galaxy NGC 3109 has shown that this galaxy and the dwarf Pneumatic Machine galaxy came closer together around 1 billion years ago. These two galaxies of the Antlia Sextans group are thought to be in a tidal gravitational interaction. The Pneumatic Machine dwarf galaxy is located 4.17 million light-years from us in the constellation of the Pneumatic Machine, as its name suggests. It is sometimes classified as a spheroidal dwarf galaxy, sometimes as a spheroidal to irregular transitional dwarf galaxy, and sometimes as an elliptical dwarf galaxy. It contains stars of varying ages, with the youngest concentrated in the center and the oldest on the periphery. The Antlia Sextans group also includes the Sextant A galaxy, an irregular galaxy, 5,000 light-years across, with a distinctive square shape. At least it's the square shape it appears to us from Earth. The Sextant B galaxy, which forms a pair with the Sextant A galaxy, is also an irregular galaxy. It lies just outside what is considered the boundary of the local group, and is moving away from the Milky Way at a speed of 300 kilometers per second, or 186 miles per second. It is one of the smallest galaxies in which planetary nebulae have been observed. At least 5 have been identified. Finally, the Leo P galaxy is a small irregular galaxy in the constellation Leo. It is very distant, around 5.3 million light-years from us. When it was discovered in 2005, scientists thought it was a high-speed cloud. It wasn't until 2013 that its nature as a dwarf galaxy was confirmed. The Leo P galaxy is home to one of the most metal-poor environments in the local universe, with a very low metallicity of just 3% that of the Sun, and stars containing 30 times fewer heavy elements than the Sun. In fact, the Leo P galaxy is similar to primitive galaxies. It is one of the smallest and faintest star-forming galaxies in the local group, with a total luminosity 440,000 times less than that of the Sun, and a stellar mass only 560,000 times that of the Sun, which is low. It therefore contains relatively few stars, and yet it's one of the few galaxies in the local group or in its immediate vicinity, if you consider that it's not part of it, that is currently still forming stars. Does that surprise you? The truth is, its star formation rate is very slow, equivalent to one solar mass every 20,400 years. No wonder then that it contains so few stars, even though it has been forming stars steadily for at least 4 billion years. We've now completed our tour of local group galaxies. However, it's important to remember that the local group isn't all galaxies and stars. Let's explore the local group's remarkable objects. Let's start with the Smith cloud. Does the name ring a bell? It's a high-velocity gas cloud with a mass 1,000,000 times that of the Sun. High-speed gas clouds like the Smith cloud are of vital importance in the local group. When they fall into the disk of a galaxy, they add baryonic matter to the already diluted matter present in the disk. Baryonic matter is made up of composite particles known as baryons. More concretely, baryons are the electrons and protons that make up the atoms of all observable molecules and structures in the universe. Stars, for example, are made up of baryonic matter. You can see where we're going with this. High-speed clouds, by adding matter essential for star formation to galaxy disks, will help maintain the galaxy's star formation rate. The Smith cloud is traveling at 870,000 kilometers per hour, or 540,000 miles per hour, towards the Milky Way. It is therefore expected to collide with our galaxy in around 27 million years' time, well before the predicted collision with the Andromeda galaxy. This impact could trigger an explosion of star formation. The most recent studies of the Smith cloud suggest that it formed on the periphery of the Milky Way before being ejected some 70 million years ago. But scientists still don't know how this happened. The Magellanic Current is another notable high-speed cloud of the local group. This is the matter bridge in the wake of the large and small Magellanic Clouds. It moves at a speed of 400 kilometers per second, or 250 miles per second, well above the speed at which our galaxy is moving. We don't really know how it formed, but it's assumed that tidal forces between the Milky Way's two satellite galaxies are behind it. In 2010, it was established that it would cover a distance of 600,000 light-years, which is much longer than researchers had previously thought. From this information, scientists have deduced that the Magellanic Current may have formed around 2.5 billion years ago, when the Magellanic Clouds passed close to each other. The Magellanic Current is of interest to scientists who study it to better understand the interaction of high-speed clouds and our galaxy. Before ending this journey, let's take a look at one last unusual local group object, known as the Unicorn Ring, or Unicorn Current. We already caught a glimpse of it earlier during our exploration of the Big Dog Galaxy. This long filament of stars discovered in 2002 surrounds the Milky Way over a length of 200,000 light-years at a distance of around 53,800 light-years. We don't really know the origin of the unicorn ring. It could be the remnants of the merger of two galaxies, either the merger of the Dwarf Great Dog Galaxy with the Milky Way, or the merger of the Dwarf Sagittarius Galaxy with our own. In any case, according to a 2011 publication in the respected journal Nature, the merger of the Milky Way and the Sagittarius Dwarf Galaxy could create such rings. Another hypothesis asserts that the unicorn ring is not actually a ring, but simply an overdensity. Overdensities are said to be common in galaxies with distorted flaring disks, such as the Milky Way. In other words, this is not an independent structure, but a ripple in our galaxy's disk. This hypothesis was invalidated by observations made by the Anglo-Australian telescope in 2007. According to these observations, a deformed disk could not create the structure we observe. For that to happen, the disk would have to erupt, or the cause could be external to our galaxy. In short, we don't know much more at present, but scientists are continuing to investigate the origins of this original local group structure. Our journey is drawing to a close. It's tempting to explore the universe even further. You're probably wondering what lies beyond the local group. Our neighboring galactic group is the IC342, Maffei group, which has the same structure as the local group. In other words, it's made up of two structures organized around massive galaxies. The first is IC342, or Caldwell 5, an intermediate spiral galaxy in the Giraffe constellation, 11.4 million light-years from us. The second is actually a pair of galaxies, Maffei 1 and Maffei 2, both located in the Cassiopeia constellation. Each of these two structures has 9 known satellite galaxies. Like the local group, the IC342 Maffei group is part of the Virgo supercluster. The local group and the IC342 Maffei group are only a tiny part of our universe. There are many other groups, such as Stephan's Quintet, a group of 5 galaxies located in the Pegasus constellation and remarkably photographed by the James Webb Telescope, or Robert's Quartet, a group of 4 galaxies in the Phoenix constellation. And in a few billion years' time, all this will have changed again. The dynamics of the local group itself are changing, albeit on such a large timescale that we don't realize it. With the merger of its 2 main galaxies, the local group will look decidedly different in 4 billion years' time. In place of the 2 substructures of our galaxy group, we'll have a large elliptical galaxy, whose other nearby galaxies, notably the Triangulum galaxy, will become satellites. It's also possible that the local group will one day merge with the Virgo cluster, the nearest large cluster of galaxies. But we're talking here about a future where the Earth will probably no longer exist, devoured by our sun, then transformed into a red giant. In the meantime, we have plenty of time to continue observing the local group and its surroundings, and to learn a little more every day about the universe and its formation.